C'est prêt, on peut commencer quand tu veux.
It's a pleasure for me to introduce Claude Lebron, which is going to talk about his last series of lectures on curvature in the balance.
Well, it's sort of sad to be at the end of the week. This has been a wonderful conference. It's been so nice to see so many old friends and make new ones. And I found this very stimulating. I hope that my own lectures have been interesting and useful. So I'd like to begin today by reminding you of the special character of dimension 4. The crucial thing is that on an oriented Riemannian four manifold, there is a splitting of the bundle of two forms into the bundles of self-dual and anti-self-dual two forms. Those are the eigenspaces of the Hodge-Star operator. And because Hodge-Star is always conformally invariant in the middle dimension, this splitting of two forms on a four manifold is conformally invariant. I've described it as depending upon the metric, but in fact only depends on the conformal class. We also saw that a consequence of this splitting is that you can decompose the curvature tensor into four pieces: the scalar curvature, the trace-free Ricci curvature, the self-dual Weil curvature, and the anti-self-dual Weil curvature. And those last two pieces of the curvature, which add up to the Weil tensor in the more naive sense, are both conformally invariant. So it is dimension 4 is the only dimension in which there are four irreducible pieces of the curvature tensor. In high dimensions, there are only 3, and in dimension 3, there are only 2. Dimension 3, there are only 2, and in dimension 2, there's only 1. So on a four manifold, if we assume now our manifold is smooth, compact, oriented, and without boundary, then we have four interesting quadratic curvature functions on it. These are all scale invariant. They're all invariant under multiplying the metric by a constant. The last two, though, are actually conformally invariant. If you multiply the metric by an arbitrary function, it doesn't change the last two. On the other hand, these functionals are not genuinely independent on a fixed manifold, because we saw that there were two Gauss-Bonnet type formulas. There's literally the generalized Gauss-Bonnet in dimension 4, which expresses the Euler characteristic in terms of an integral of a particular linear combination of these four basic pieces of the curvature. And there's also the signature formula related to the fact that the signature is 1/3 of the first Pontryagin number of the four manifold, which is expressed, in fact, in terms of an integral of the difference between self-dual Weil squared and anti-self-dual Weil squared. So using those two facts, as long as you know which manifold you're talking about, you can express implicitly any quadratic curvature functional is really built out of two basic ones, which I'll take to be the integral of the scalar curvature squared over 24 and the pointwise norm of the self-dual Weil curvature squared. So for example, in the last lecture, I introduced the so-called Weil functional, the L2 norm squared of the full Weil curvature. And as an example of the fact that these functionals determine any such expression, in fact, you only have to know self-dual Weil squared to be able to read off what the Weil functional is. And so it's an important point that when you're studying this second functional, it's essentially equivalent to the Weil functional. For various technical reasons, it will be more convenient to to use this rather than the Weil curve, the Weil functional in this more primitive or more naive sense. So so the Weil functional, of course, is, it measures it gives you a quantitative measure of how far a metric is from being locally conformally flat, and using this expression for the Weil functional, one can then read off how far a metric is from being locally conformally flat, just knowing the integral of Weil plus squared. So the theme of today's lecture is how do these functionals compare in size for specific classes of metrics on interesting four manifolds. Hence the title of the series, Curvature in the Balance. How do these two basic curvature functionals compare? So yesterday I discussed the Kähler case at some length, and we saw that if you have a Kähler manifold, so a complex manifold of complex dimension 2, and you have a Kähler metric on it, and you give M the orientation determined by the complex structure, then in fact, there's a pointwise equality between scalar curvature squared over 24 and W plus squared. Again, this is a surprising thing because W plus squared is, with a conformal weight, it's a conformally invariant kind of object. W plus is a conformally invariant tensor. Whereas the scalar curvature is not conformally invariant by any stretch of the imagination. But the point is that this is a statement about Kähler manifolds, and the Kähler condition is not conformally invariant. So, so in particular, when we look at the integrals of these two curvature quantities for Kähler metric, we get the same thing. So it's natural to ask if there's anything going on for more general metrics. And there are many contexts where this turns out to be a very interesting question. So for example, let me begin with a result of Matt Gursky's. It actually first appeared in a paper I wrote with Matt, but it's his idea, and it's simply a matter of the rate at which certain journals publish their articles. So the idea first appeared in the paper that appeared second. So suppose you have a compact-oriented Einstein manifold with positive scalar curvature, and assume that it's not an irreducible symmetric space. So in fact, that there are two symmetric spaces we specifically want to exclude here. We want to exclude the four sphere with its usual symmetric space metric, its metric of constant curvature, and we want to exclude the reverse-oriented version of CP2 with the Fubini-Studi metric. All right, so in fact, this is a little bit overkill. The irreducible oriented symmetric space as well, you'd have these and the oppositely oriented CP2, which is not a problem for this theorem. All right, so then the statement is that this Weil functional, the integral of W plus squared, is greater than or equal to the integral of the scalar curvature squared over 24. And you get equality if and only if the metric is locally Kähler-Einstein. So locally Kähler-Einstein here has a more concrete meaning. It's saying that after, at worst, passing to a double cover of the manifold, it becomes a Kähler-Einstein manifold. So you can find certain Kähler-Einstein manifolds, for example, S2 times S2, with its standard Einstein metric, that has a fixed point free isometry given by applying preserving the orientation. Just take the antipodal map on both factors at the same time. That gives you a Z2 action where the quotient is an oriented manifold. You can apply this theorem. It's not it's not an irreducible symmetric space, so you don't have to. So the theorem really applies. Of course, the metric is locally Kähler-Einstein. It becomes double Kähler-Einstein after you pass to a double cover, and of course, in that case, the inequality is saturated. So I'll explain in a moment where this remarkable inequality comes from. But I also want to contrast it with an inequality that I proved a few years before that. So the first version appeared in a paper in 1995, but there are some extra facts I'm going to throw in order to formulate it in the following way. So in a certain sense, the full version of this theorem as I will present it would have been impossible before about 2009. All right, so suppose that we have a smooth compact four manifold that admits a symplectic form, but which does not admit an Einstein metric with positive scalar curvature. So last time we saw that there were very few manifolds that admitted both an Einstein metric with positive Einstein constant and a symplectic form. And we want to exclude those. So what we're actually excluding here are the del Pezzo surfaces. So you're assuming that you have a four manifold which carries a symplectic form, but it's not a del Pezzo surface. Then, so in particular, if you had an Einstein metric on such a manifold, you already know that its Einstein constant has to be less than or equal to 0, right? Because we explicitly have said it doesn't have a positive lambda Einstein metric. Then with respect to the symplectic orientation, then any Einstein metric on this manifold satisfies the opposite inequality. The integral of scalar curvature squared over 24 is greater than or equal to the integral of W plus squared. And equality occurs if and only if the metric is Kähler-Einstein. All right, so these two results, in these two different results, the balance between these basic functionals is opposite, but also the sign of the Einstein constant that occurs is opposite. So there's this very curious situation where there seem to be some systematic trends on the relative size of this Weil functional and the scalar curvature functional, which is related to the sign of the Einstein constant. All right, so actually, in order to read, so the usual way of presenting these inequalities in the published papers does not present the phenomenon in this way. Instead, it's usually formulated in terms of this important topological invariant, twice the Euler characteristic plus 3 times the signature. That number sounds very arbitrary, and in fact, many of the theorems about this invariant were just discovered by, well, you stare at the you stare at the Euler characteristic and signature integral formulas, and then notice that if you take this combination, you've managed to kill off the presence of W minus. But actually, this is not an arbitrary number at all, and this is not this actually a very good way of proving this formula is instead to first observe that this number is the first Pontryagin number of the bundle lambda plus. And actually, there's a very good way in dimension 4, rather than taking the conventional proofs of Chern-Gauss-Bonnet and the signature formula, you could first prove this. And just saying, well, it's what you're calculating. You have to also make a little observation that a priori that number is the same as the first Pontryagin class of lambda plus, and therefore is determined by the curvature of lambda plus. And it turns out that these are the only three contributors to the curvature of lambda plus. All right, so in fact, then when you're going to make statements about how does the integral of the scalar curvature squared compared to the integral of W plus squared, in fact, so in the Einstein case, this last term, the trace-free Ricci curvature term, which is the only one that appears here with a negative coefficient, in the Einstein case, this only involves the integral of scalar curvature squared over 24 and the integral of W plus squared. And so saying that the integral of W plus squared is greater than or equal to the integral of scalar curvature squared over 24 is the same as saying, for an Einstein manifold, it's the same as saying that the integral of W plus squared is greater than or equal to a third of this topological invariant. And similarly, saying that the integral of the scalar curvature squared is bigger than the integral of W plus squared is the same as saying that the integral of the scalar curvature squared over 96 pi squared is greater than or equal to 1/3 of 2 chi plus 3 tau. And it's actually in this context, when in the proof involving Seiberg-Witten theory involves the fact, remember I explained that there were lower bounds for the integral of the scalar curvature squared when the Seiberg-Witten invariant was non-zero. And that's the source of this, this inequality in this for symplectic, for manifolds that both have for Einstein manifolds that happen to also carry a symplectic form. All right, so let me just rewind for a moment and look at Matt's result. So the method for proving this is quite beautiful. It has to do with the fact that an Einstein manifold, as a consequence of the differential Bianchi identity, has the property that its self-dual Weil tensor is co-closed as a bundle-valued 2 form. A different way of saying it is the divergence of W plus is 0. So this, by the way, that divergence is essentially the thing that I mentioned before, the Couton tensor, and that vanishes for an Einstein manifold. So it's a piece of the Couton tensor, actually. This is a Dirac type equation, and you always have a Weizenbach formula. That's for anytime you have something that's killed by a Dirac type operator, there's a formula that says, well, the Bachner-Laplacian applied to that field, whatever it is, in this case it's W plus some curvature term is equal to 0. But here, W plus is both the field, the thing that's in the kernel of the operator, but it's also a piece of the curvature. So you end up with terms that are nonlinear. So here I've really taken that Weizenbach formula to take its inner product with W plus, and you would expect, I mean, naively, well, it's going to be, you know, W things that are quadratic in W plus times some curvature, but in particular, you end up with a cubic term because you have the Weil tensor acting on itself. All right, so this is a remarkable Weizenbach formula that's been was really emphasized by Andrei Derjensky. And if you look in the book by Bess, or allegedly by the non-existent person Bess, on Einstein metrics, really by Berger's school, then you'll find that there's a long discussion of this particular Weizenbach formula. So Matt used this in a very interesting and novel way. What he observed is that if you look at, there's a kind of generalized scalar curvature where you take the usual scalar curvature and minus twice, so minus the square root of 24 times the pointwise norm of W plus. And you could ask, how does that vary as you change the metric? Well, the formula for the way that this kind of object changes under conformal rescaling is exactly parallel to the usual Yamabe formula for how does the ordinary scalar curvature change. there's a trick introduced by Neil Trudinger that so before the Yamabe problem was solved, when Trudinger first realized, oh my gosh, there's a mistake in Yamabe's paper, he began to fix it by first making the observation that if you take this Yamabe Laplacian, take its lowest eigen, take its lowest eigen value, and then take the lowest, take an eigenfunction for that lowest eigenvalue, there's a general minimal principle that says that for the lowest eigenspace is one-dimensional, and the eigenfunction has no zeros. It's like saying for the lowest, when you tap a drum and watch how it vibrates, the lowest note does not have a nodal set. It vibrates without zeros. You can then use that as a conformal rescaling choice. When you do that, you've arranged either for the ordinary scalar curvature or any generalized scalar curvature like this, you can always find a metric for which that quantity, in the conformal class, there's always some metric for which that doesn't change sign. It's either everywhere positive or everywhere negative or identically zero. All right, so on the other hand, what Matt then observed was that if this quantity was positive, you'd have a contradiction from this formula. And therefore, there must be some metric in the conformal class for which this is non-positive. Now you integrate, use Cauchy-Schwarz, and you get this inequality initially for your particular metric, but then when you pass to the Yamabe minimizer, this size can only get smaller. By contrast, this theorem that I proved that is stated here in terms of symplectic manifolds, secretly what's really going on is that it has to do with having non-zero Seiberg-Witten invariant. There's some subtleties in the case when B plus is 1. But the real point in terms of how to prove an inequality like this is that you get an inequality out of Seiberg-Witten theory between an integral of the scalar curvature squared and a certain multiple of 2 chi plus 3 tau, which is also C1 squared of your spin C structure. All right, so you use the Weizenbach formula for the Seiberg-Witten equations. The first thing is you know, in the symplectic case, it's by result of taubes that there will have to be a solution of the Seiberg-Witten equations for your given metric, and then you can use the Weizenbach formula and eventually prove this inequality. All right, so it's interesting to ask for Kähler metrics, we get that these two functionals are equal. And we find for Einstein metrics, there are these very interesting systematic trends. I mean, it's not like you can expect there's some universal inequality. It depends on specific choices of extra hypotheses. But so the most naive thing to say, well, why don't we ask this for just general Riemannian metrics? Could that be an interesting question? Well, it's a silly question, actually. It's a completely silly question. And the reason is that this Weil functional is conformally invariant. And on the other hand, we saw that in our discussion of the Yamabe problem, the integral of the scalar curvature squared depends wildly upon your choice of conformal factor. So, so in fact, in any conformal class, you can make, by choosing a highly oscillatory conformal factor, you can make the integral of, you can make the Einstein-Hilbert functional go to infinity, and then the L2 norm of the scalar curvature is even bigger than the Einstein-Hilbert functional. So you can always find metrics in any conformal class for which the integral of the scalar curvature squared goes to infinity. And since the integral of W plus squared is conformally invariant, you can always find any conformal class. I'm sorry, this is the wrong inequality. Sorry, that's supposed to point the other direction. Okay, so you can, I was typing that last night and I just got it the wrong way. So the integral of the scalar curvature squared you can certainly arrange for that to be huge compared to the integral of W plus squared. On the other hand, we also saw in our discussion of the Yamabe problem that if you take any metric you like and then look at the Yamabe minimizer in that same conformal class, if it then the Yamabe minimizer has integral of scalar curvature squared, typically less than for a given metric, and the Yamabe minimizer has constant scalar curvature. So if you start with a metric that has non-constant scalar curvature, and then you choose the Yamabe minimizer in that class, in that conformal class, the integral of the scalar curvature squared has to go down. So in particular, if you start with any compact complex surface of Kähler type, one that carries Kähler metrics, well, most Kähler metrics do not have constant scalar curvature. I mean, constant scalar curvature Kähler metrics do exist with a certain, but they're kind of rare. They're very odd birds. So just take any Kähler metric which has non-constant scalar curvature, take its Yamabe minimizer, and you've just produced something where the integral of the scalar curvature squared over 24 must go down. But for the Kähler metric, these two functionals are the same. And so, in fact, so for many of the manifolds of most interest for my particular obsession, there are certainly always Riemannian metrics where the balance goes either way. And it has, there's nothing systematic you can say for general metrics. So this says that the question is not an interesting question for general metrics. It only becomes sensible if you restrict the question to some class of metrics where conformal scaling is essentially ruled out. So for example, we saw for Kähler metrics, where you can't rescale a Kähler metric, given the Kähler metric, you've got some very interesting systematic property, namely those two functionals are the same. We saw that for Einstein metrics, there are very interesting systematic statements one can make. Another interesting class of metrics where you can't really conformally rescale are the so-called almost Kähler metrics. I mentioned those before. In the Kähler case, there's a relationship between the metric and a certain harmonic two form, which happens to be parallel in the Kähler case. So more generally, what you can take, you can imagine a metric that's related to a symplectic form via a choice of almost complex structure, which is no longer required to be integrable. And so you get a very large class of Riemannian geometries called almost Kähler metrics. As long as you have, if you have a self-dual harmonic two form, which is everywhere non-zero, you can just make, there's a preferred conformal change, so you can make its length constant, namely equal to the, make its length equal to the square root of 2 at every point, then you're looking at an almost Kähler manifold. There turn out to be interesting systematic trends for this problem, for this kind of question, for almost Kähler manifolds. So one way of getting an interesting question is to somehow restrict to an interesting class of metrics where you can't conformally rescale. But another thing you could do is just tweak the problem in order to make it conformally invariant. And the discussion of that Gauss-Bonnet-like expression 2 chi plus 3 tau, or if you like the first Pontryagin number of lambda plus, shows you how to get a conformally invariant problem. So, so you could, rather than comparing the integral of W plus squared to the integral of scalar curvature squared over 24, you can compare it to the integral of scalar curvature squared over 24 minus trace-free Ricci curvature squared, which is the remaining piece of that. It's the piece of that Gauss-Bonnet type formula that does not involve W plus. So this integrand here is one that has been extensively studied by people like Matt Gursky and Alice Chang and Paul Yang, because it's often referred to as sigma 2 of the Schouten Ricci curvature. All right, so one conformally invariant version of the problem is to compare the integral of w plus squared with the integral of sigma 2, and that's equivalent to asking whether the integral of w plus squared is larger than a certain multiple of 2 chi plus 3 tau. So as we just saw, in particular, you have an interesting lower bound in those cases where one has an anti-self-dual metric, and in the case of CP2, Yat-Sun Poon first proved in his thesis that there is, in fact, only one self-dual metric with positive Yamabe constant on the on CP2. This argument. So this is the same, of course, as just asking that your conformal class has a positive scalar curvature representative. Whose proof is beautiful but very complicated. It builds on previous work of Hitchin, and the point is that Poon directly shows that you can use the Hirzebruch index formula for predicting how many holomorphic sections of a line bundle you have in terms of a lower bound being given in this case by the index of a holomorphic line bundle, to show that in fact the twistor space is actually an algebraic variety, and eventually you show that it is this flag manifold. Matt Gursky found a much simpler proof much later, and it's related to some of the theorems I'm telling you about today. So whereas Poon's proof is a very, very long, detailed piece of algebraic geometry, this is sort of a very short analytic observation. All right, so on CP2, one actually does know what the infimum of the Weil functional is, and in fact, it coincides with a lower bound one would expect for a different reason. So around the same time as Poon was doing his work on CP2, Osamu Kobayashi asked what happens on some other familiar manifolds, though. So he, in particular, was interested in asking what's the infimum of the Weil functional on S2 times S2. Now, this is a manifold that certainly cannot admit a self-dual metric. And the reason is that our signature formula tells you that if W minus is 0, then W plus is equal to 0 also, because S2 times S2 has an orientation reversing diffeomorphism. Its signature, therefore, is 0. And so you'd be asking whether you could find a conformally flat metric on S2 times S2. And of course, this is a compact, simply connected manifold. But Nico Kuiper proved in the late 1940s that if you have a conformally flat, simply connected manifold of dimension greater than or equal to 3, then in fact it has to be the round sphere, the standard sphere with its standard conformal structure. The reason is that there's always a developing map from the universal cover to the sphere, where the group, everything is defined up to Möbius transformations. So actually, I mean, the statement, of course, is true even in dimension 2, but the proof is completely different. The uniqueness of the conformal structure on S2 does not go this way, because there are lots of local conformal transformations in dimension 2. There are very few in higher dimensions. So anyway, this contradiction shows you that S2 times S2 is an example of a manifold that cannot admit a self-dual metric. So you know what might be the infimum of the Weyl functional on this manifold? Kobayashi gave some interesting evidence in favor of the conjecture that it's actually there's actually a minimizer, namely the standard Kähler-Einstein metric, the one you get by taking the product of two standard unit two spheres. So the evidence he found was fairly weak, but in particular, he did a nice calculation to show that it's a local minimum of the functional. And then he tested it out just, for example, on Kähler metrics. And it's not very easy to show that on Kähler metrics, and it minimizes that, but that doesn't really, it's not much evidence. Still, this is a very interesting conjecture. So what's the common feature between the previous case that we considered, CP2, and S2 times S2? Well, the point is that the thing that's actually the minimizer in the CP2 case, and the thing that's the proposed minimizer for S2 times S2, is that they're both Kähler-Einstein metrics with positive Einstein constant. And so a very good question is, if you have a, pursuing this lead actually goes to very interesting places. And so I'll next, so I don't think we need an intermission now. We've already had too many. A natural generalization, since that story was about Kähler-Einstein metrics with positive scalar curvature, one might imagine that in complex dimension 2, real dimension 4, that actually Kähler-Einstein metrics with positive lambda are minima of the Weyl functional. This is oddly different from the negative case. In the negative case, they minimize the integral of the scalar curvature squared. And that's Seiberg-Witten theory gives you a very clean proof of that. But there's no analogous tool that one can use easily in the positive case. One would hope that it's the Weyl functional that's minimized by these metrics. So a generalization of Kobayashi's conjecture is, it says if you take any Del Pezzo surface, and you look at the conformally Kähler-Einstein metric that is determined by that complex structure, that metric is actually a minimizer of the Weyl functional, and maybe it's the only kind of. So you generally do have a moduli space of such things. If you sum Del Pezzo surfaces, you can deform the complex structure to get a family of Kähler-Einstein metrics. In the ones where the metric is not Kähler-Einstein but just conformally Kähler, then it turns out that the complex structure is always rigid in those cases. You only get one metric. So we saw last time that a Del Pezzo surface is by definition a compact complex surface for which the anticanonical line bundle is ample. In other words, it's a Fano manifold, and the manifolds that arise this way are blow-ups of CP2 at 0 to 8 points, or CP1 times CP1. And we also I also discussed the theorem that every Del Pezzo with a fixed Del Pezzo complex structure admits a unique, a geometrically unique conformally Kähler-Einstein metric. So the conjecture is that those metrics are always absolute minimizers of the Weyl functional, and one might even hope that perhaps they're the only ones. So I'm going to now tell you about some persuasive partial results in this direction. But the problem is still open. These partial results do not completely solve the problem. They merely give us some very, I find, compelling evidence in favor of this conjecture. So so Matt Gursky made a huge contribution to the problem, and I don't think he'd ever heard of Kobayashi or seen his paper, but he actually proved far more than Kobayashi had dreamt of being able to show. Suppose you take a smooth compact four-manifold, compact-oriented four-manifold with B plus non-zero, right? So in other words, it's saying that the intersection form is not negative definite. There's a positive direction if you like, for any metric, there is at least one self-dual harmonic two-form. Then any conformal class with positive Yamabe constant satisfies this desired inequality, that the lower there's a uniform lower bound for the integral of w plus squared on all positive Yamabe conformal classes that is exactly this the desired multiple of 2 chi plus 3 tau. And moreover, you can get equality in this if and only if the metric is Kähler-Einstein with positive Einstein constant or positive scalar curvature. So in particular, I was mentioning some other possible minimizers that were not Kähler-Einstein, but merely conformally Kähler. And when you calculate the Weyl energy for those, it's bigger than this lower bound. You don't saturate this lower bound. It would have to be some extra source of a little gap. Okay, but so Matt's theorem here shows that any Kähler-Einstein metric with positive lambda in complex dimension 2 or real dimension 4 actually does minimize the Weyl functional. And in fact, those are the only minimizers up to conformal changes where the Yamabe constant is positive, where the conformal class has a among all conformal classes which are represented by metrics of positive scalar curvature. All right, so in particular, just going back to the question that Kobayashi asked, on S2 times S2, this gives you a huge region in the space of conformal classes where you know that you have an absolute minimizer. I mean, it confirms everything that Kobayashi was actually able to prove, but it just proves a whole lot more. You have this huge open set. But the difference between this assertion and what one knows about CP2, for CP2, because it has a self-dual, the Fubini-Studi metric is self-dual, you know it's an absolute minimizer among all conformal classes, independent of any discussion of scalar curvature. And so the open part of this question for on a del Pezzo surface has to do with conformal classes which don't have positive scalar curvature metrics in them. So the thing to notice, though, is also, I mean, this is an amazing result. It's very, very useful, but it has the one odd feature. It actually works on lots and lots of manifolds. You merely have to have B plus non-zero, but you still get such a universal inequality, which is typically not saturated ever. If as long as you restrict your attention to metrics with positive Yamabe constant. By the way, I mentioned before that that Matt had given a different proof of the uniqueness of the self-dual conformal structure on CP2 with positive scalar curvature, and it follows from this, right? It's because the signature formula tells you if W minus were 0, you would know what the integral of W plus squared was, and it saturates this inequality. So this is a fantastic theorem, but on the other hand, it doesn't quite answer the question I'm asking, which is about all conformal classes. And the odd thing also is that it doesn't just apply to del Pezzo surfaces. It applies to anything where the intersection form has a positive direction. But it tells you nothing about, for example, conformal classes with negative Yamabe constant. Matt's method here is again based on a Weizenbach formula, but it's instead the Weizenbach formula for harmonic self-dual two forms, which is an extremely important general Weizenbach formula. And again, the trick is that you could show that if you look at that same kind of perturbed scalar curvature as before, there has to be a conformal in any conformal class. There has to be a metric where it doesn't change sign. You'd have a contradiction if the sign of that was positive and therefore you, by the same kind of argument as before, even though using a different Weizenbach formula, the method of proof is parallel. They're very similar proofs. So I now want to tell you about a different result that's specific to the Del Pezzo surfaces, and it again uses harmonic self-dual two forms, but the methods are quite different. So let me make a definition here. I want to say that a conformal class on a smooth-oriented compact four manifold is of symplectic type if and only if there exists a self-dual harmonic two form for that conformal class, which is everywhere non-zero. Okay, so you always, if B plus is non-zero, you certainly know you have self-dual harmonic two forms, but it's a very rare thing for such a thing not to have a zero. When it doesn't, if it doesn't have a zero, self-duality turns out to imply that it's a non-degenerate two form. It would be a closed non-degenerate two form. That's a symplectic form. So in other words, this is exactly the same as saying that you have a symplectic form, which is a harmonic self-dual two form for your conformal class. So in fact, every symplectic form manifold can be thought of as arising by this. You can always choose, given a symplectic form, you can always choose a metric for which the symplectic form becomes self-dual, and then it is harmonic for that conformal class. So what you can, so in this situation, there's a preferred representative different from the typically different from the Yamabe representative. You can normalize this form by rescaling the metric to have length identically equal to the square root of 2, and that makes the manifold into a so-called almost Kähler manifold. So there's an almost complex structure such that which intertwines the metric and the symplectic form. And on the other hand, so the reason it's called almost Kähler is that this almost complex structure is typically not integrable. So using such symplectic, so given a symplectic manifold, Gromov realized that one could get powerful results that were kind of parallel to things in algebraic geometry by studying these almost complex structures that are adapted to the symplectic form. On the other hand, so if we think about this as a method, it's very specific. This would not work in higher dimensions. In higher dimensions, this almost Kähler condition is very rare in higher dimensions. Here, what one finds in four dimensions, if you take let's, for example, start with a Kähler manifold, perturb the conformal structure a little bit, you always get something that after rescaling the metric gives you an almost Kähler metric. So the things that are conformally almost Kähler are open in the set of conformal, in the conformal classes of on Riemannian manifolds. This is an open condition. In a way, you can think of it as analogous to the open condition of demanding that the Yamabe constant be positive. And so this is open because as you vary the metric, harmonic forms vary nicely. Okay, so in 2015, I showed that if you have the underlying smooth-oriented four manifold of a Del Pezzo surface, then any conformal class of symplectic type satisfies this same inequality for the self-dual Weil curvature, the same one that one gets in Gursky's theorem. And again, equality occurs here if and only if the metric is, if the conformal class is can be represented by a Kähler-Einstein metric with positive scalar curvature. So this recovers Matt's inequality, but it's for a completely different open set of conformal classes. The two open sets overlap, but they are distinct. You can find metrics that are in one and not the other. One is not contained, one of these open sets is not a subset of the other. And in particular, among the conformal classes of symplectic type, most of them have very negative Yamabe constant. You can find sequences, easily find sequences of such conformal classes where the Yamabe constant goes to -infinity. So this starts to smell like, well, it can't have to do with positive scalar curvature if you're on a Del Pezzo surface. So this inequality, at least for these manifolds, starts to seem like it should be something more general. This is not definitive. We've merely shown that there are two very interesting large sets of metrics on which you get this inequality. One where you have a condition on the scalar curvature, another where you have a condition on the behavior of self-dual harmonic two forms. So the method has to do with some remarkable facts in almost Kähler geometry. So in particular, when you look at the integral of a certain combination of the scalar curvature and the component of W plus in the direction of the symplectic form, it turns out that you have there's a formula on a Kähler manifold. The integral of the scalar curvature turns out to be expressible in terms of the first Chern class and the symplectic form. It's sort of, this is the generalization. For Kähler manifolds, there's a generalization of two-dimensional Gauss-Bonnet. For generic metrics, integral of scalar curvature sort of doesn't mean anything. But on a Kähler manifold, you could say what the integral of scalar curvature is just in terms of the first Chern class and the Kähler class. But this generalizes to the almost Kähler setting. It's just that the thing that you're integrating now involves a Weil term as well as a scalar curvature term. And from this, you can, in particular, you can show that the Weil piece is actually bigger than the scalar curvature piece there. You get a lower bound for Weil just out of this. The key thing is that on Del Pezzo surface, no matter, so if you have something which is diffeomorphic to a Del Pezzo surface, you have any symplectic form on it, you take this component is a priori positive. So that gives you and now you can play with Cauchy-Schwarz and so forth. I had mentioned before, so the basic Gursky inequality does not say anything about metrics that are conformally Kähler, but not Kähler-Einstein. Einstein metrics that are conformally Kähler, it's a more complicated story. So on CP2 blown up at 1 or 2 points, we have such metrics, whereas we have no Kähler-Einstein metric. You have to step out of cases where you could saturate this inequality. What happens in this case is that you can still prove on these manifolds that you get a somewhat better estimate if you restrict to metrics which not only are symplectic type but also are invariant under a certain two-torus action. They're toric metrics. It's only in that case that one knows how to generalize the Futaki invariant to the symplectic world. But I hope that maybe this will eventually at least work for general metrics of conformal classes of symplectic type. So that's why I made that more general conjecture about that, not just for Kähler-Einstein metrics, but also more generally for conformally Kähler-Einstein metrics. However, this argument only works for Del Pezzo surfaces. It's because having a symplectic form, having positive scalar curvature metrics, or having the right sign of C1 dot omega will only, and ultimately having this quantity is positive, that actually cuts you down to a very small class of manifolds, the Del Pezzo surfaces. All right, so the question that is natural to ask is, so here there are two proofs of kind of, the same inequality, albeit for different classes of metrics, but Matt's argument works in great generality, anything that has positive scalar curvature metrics and which has B plus non-zero. Whereas this works for a very small special class of four manifolds. So one might ask, what happens if we step outside the Del Pezzo realm for this question about metrics with negative Yamabe constant? Could this inequality still hold for general conformal classes? So Kobayashi's conjecture originally was, he was just looking at S2 times S2. That's an interesting spin manifold. If you look at spin manifolds in dimension 4, which are simply connected and could admit positive scalar curvature metrics, well, up to homeomorphism, you can get the connected sums of S2 times S2s. Positive scalar curvature would, after all, force the A hat genus, the signet, which is the multiple of the signature, to vanish. So you can't have something like a K3 surface or connected sums with K3 surfaces. So for simply connected things, it's sort of the first natural thing to do is, well, what if we look at the smooth manifolds you get by taking connected sums of S2 times S2s? What happens on these manifolds in the Yamabe negative realm? And the answer is disaster. Namely, if you take a connected sum of sufficiently many S2 times S2s, there are conformal classes on it that violate that inequality. So these, of course, so if there's only one S2 times S2, it's a del Pezzo surface. This argument, I'd like to think that this works for connected sum of two S2 times S2s. But unfortunately, what it simply says is if you have a billion, actually, I could try to get an effective number, but there's a sufficiently large integer so that if the number of copies is at least that integer, then there are things that violate this inequality. And actually, it shows that you can find things. It's not saying that this is close to zero, but it's maybe half the size of this other side. It's constructive, yeah. No. So I'll show you I'll indicate in a moment what the method of proof is. See, the thing is that you hope on S2 times S2 any conformal class is going to satisfy your inequality, and if you start making connected sums of those things, the inequality would still hold. But the point is that there are geometries on these connected sums of S2 times S2s that are very wild. And so that's a particular class of simply connected spin manifold. I mean, so up to homeomorphism, these are the simply connected spin manifolds that could admit positive scalar curvature metrics. But in fact, here we're looking at a particular smooth structure. It turns out that asymptotically, well, you can always get the standard smooth structure by taking connected sums with extra S2 times S2. So the same thing, if you ask it about non-spin manifolds, the sorts of things that occur, the only topological possibilities are connected sums of CP2s and CP2 bars. But here we're talking about with the standard smooth structure, that smooth manifold. But there's a kind of there's a kind of stability I'll come to in a moment where one starts seeing the standard smooth structure when you take connected sums with enough copies. All right, so the statement here is that, again, if you have enough copies of CP2, and if the ratio of the number of copies of CP2 and CP2 bar is close to 1. The range in which this argument works is when the ratio is something like 4 to 5, 5 to 4. Then you can, then again, there are conformal classes that violate that inequality that you expect that I'm hoping will hold for general conformal classes on a del Pezzo surface. So here are some of the key ideas in the proof. The main observation is due to CTC Wall from Terry Wall from the 1960s. He proved a really important result in trying to classify four manifolds. As I pointed out in a previous lecture, there are lots and lots of smooth structures on a four manifold, typically. However, actually, if you take two different, it's enough to say you have two simply connected four manifolds which are homotopy equivalent. Actually, that means that they're homeomorphic, but he didn't know that at the time. Then if you take their connected sums with enough copies of S2 times S2, they will become diffeomorphic. So there's a kind of stable, there's a notion of being sort of stably homeomorphic, diffeomorphic. So up to taking connected sums with S2 times S2, are they diffeomorphic? That turns out to be the same question that as whether they were homeomorphic to begin with. So in particular, that means you can take some manifold that has very strange geometry that's very different from the positive world and take its connected sum. So you want to take some simply connected spin manifold, take its connected sum with its conjugate that has zero signature, take connected sum with a lot of S2 times S2s, and that will actually be for enough copies you would actually be looking at just a connected sum of S2 times S2s. All right, so here the basic building block is to have a simply connected minimal complex surface with positive signature. Now, if you start just trying to write down compact complex surfaces, we saw a particular infinite list. One thing I didn't really emphasize was that in that list, they all had negative signature. When you look at things like complete intersections of hypersurfaces in projective spaces, you're only going to see things of negative signature. Those are interesting simply connected manifolds. Bogomolov actually conjectured that a simply connected compact complex surface would have to have a negative signature. And that turned out to be wrong. So the ones with positive signature are much harder to construct. So there were people like Peters who proved the existence of a lot of such objects back in the 1980s. But there's a recent breakthrough where we now know that these are really, they exist in amazing profusion. So there were conjectures about the so-called geography of complex surfaces, what kind of signature and Euler characteristic you could get for a simply connected compact complex surface. It turns out that these can approach the Mio-Yau line. They can, in terms of signature and Euler characteristic, you can find simply connected examples which are very, very close to what you would get for this ratio if you were to look at a quotient of the ball, which has huge fundamental group. So the most naive examples of things with positive signature among complex Kähler surfaces, they tend to have huge fundamental group in the case where there's a negative Kähler-Einstein metric. But it turns out that that's just misleading. It's just that it's much harder to find these other examples. But the huge advance in the subject was made by Rouleau and Erfrua in 2015. So these do exist in great profusion, and in the argument you could just choose one. Actually, if you want to just do the case about connected sums of S2s, S2 times S2s, just take one such thing, simply connected, spin. So, and by the way, I should say in that you can choose such sequences going to the Miyoko-Yau line that are either spin or non-spin. All right, so the strategy to find the right conformal classes is you start by looking at these negative. So they might not all have, these minimal complex surfaces might not actually have Kähler-Einstein metrics, but they're all small modifications of a Kähler-Einstein orbifold called the pluricanonical model. Then just by some simple surgical techniques, you can get rid of the orbifold singularities by gluing in gravitational instantons. And the main trick is that you can take an arbitrary Riemannian manifold and just change the metric to make it literally conformally flat in some very, very tiny ball. As soon as and you can do that without changing this Weil curvature functional, except by a tiny smidgen, as small as you like. Then as soon as you have a conformally flat ball, well, you take out a smaller ball, you take a reflection, you can glue things together, connect sums. All right, so, and you do that with these negative Kähler-Einstein metrics and just the standard, for example, the standard Kähler-Einstein metric on S2 times S2. Form these connect sums. There's a kind of a little bit of tricky numerology here to see that it's related to the so-called Frobenius coin problem that you can, by just looking at connected sums like this, where you have two basic integer variables, you can arrange for you can for the Euler characteristic to be, or for the number of copies of S2 times S2s you get at the end is anything above a certain threshold. All right, so so that's the basic idea of how to prove this theorem. I was going to tell you, well, I guess I'll take just another 5 minutes. So I've been, I mean, this is the harder result that I wanted to explain today. And that it's again, everything is sort of just partial evidence. I made a conjecture about the behavior of this, about this particular lower bound for the Weil functional on Del Pezzo surfaces. And the way that you can get it for a lot of conformal classes with negative Yamabe constant is something that will only work on the Del Pezzo surfaces. And here there's some partial evidence that, well, that seems to be part of the story. We don't know that it fails on, say, S2 times S2 connected sum itself once, but if you take enough copies, it certainly fails. All right, so in the discussion today, I've talked about this question of balance, comparing, so this question about comparing the Weil functional to the scalar curvature functional. Almost Kähler manifolds came up, and we also saw this equation for harmonic self-dual Weil curvature come up in the proof of Matt's, the first theorem by Giorgi that I mentioned. So after this heavy meal, we'll have a light dessert course where we'll see these ideas come into play in a different way. So, so here I mentioned almost Kähler manifolds, and you could ask, well, what happens? So that's something which is not conformally invariant. What happens to the balance between Weil and scalar curvature on these manifolds? Well, to get a result, I want to first consider the class of almost Kähler manifolds for which the self-dual Weil curvature is harmonic. So in other words, the divergence of W plus is 0. And then it turns out that there's a nice balance result. The integral of scalar curvature squared is always greater than or equal to the integral of W plus squared, and you get equality exactly in the case when the metric is Kähler. We know for a Kähler metric, you always get equality. Among the almost Kähler metrics with harmonic self-dual Weil curvature, you get an inequality, and it's saturated only in the Kähler case. Now, you might think, well, why introduce this funny condition on the harmonicity of the self-dual Weil curvature? Maybe this is just a general trend for almost Kähler manifolds, but it certainly isn't, because in contrast, if you look at almost Kähler manifolds that have positive scalar curvature, then you get the opposite inequality. The integral of Weil squared is bigger than or equal to the integral of scalar curvature squared over 24, and you get equality exactly in the Kähler case. So one consequence is that if you have an almost Kähler manifold with harmonic self-dual Weil curvature and positive scalar curvature, it must be Kähler. Now, this is actually a generalization of a theorem that was proved, I guess, back in circa 1980 by Sekigawa on the so-called Goldberg Conjecture, which is if you have an Einstein manifold, which is almost Kähler, Goldberg, for unknown reasons, conjectured that it would have to be that it would have to be Kähler. He didn't even specify the manifold is compact, and in the non-compact case, that's certainly false. But Sekigawa proved a very interesting result that if you have initially he proved it in dimension 4 and then generalized it to higher dimensions. If you have an almost Kähler 4 manifold, which is Einstein, then it's in fact a Kähler-Einstein manifold. Here's actually, so among Kähler manifolds, the ones with harmonic self-dual Weil curvature are exactly the ones for which the scalar curvature is constant. So this is a generalization of that statement that is sort of in the setting of constant scalar curvature Kähler metrics rather than Kähler-Einstein metrics. So the proof of this little result is you can look at, again, there's a Weizenbach formula that's implied by the assumption that that W plus is harmonic. Here, I haven't taken its inner product with, this is the source of the previous Weizenbach formula that we saw before, but I'd taken the inner product with W plus. But I don't want to do that, take its inner product with W plus here. What I want to do is instead contract it with the symplectic form tensor itself. And after many calculations, one is eventually able to produce this very pretty equality that on one side just involves Weyl terms, and then on the other side involves scalar curvature times the component of W plus in the direction of the symplectic form. So to get there, one has to use, again, another Weizenbach formula that came up in the previous argument discussion was the Weizenbach formula for self-dual harmonic two forms. But an almost scalar manifold, because the symplectic form omega has constant length, you get a simpler Weizenbach formula because normally you'd have an extra term that involved Laplacian of omega squared, but omega squared is constant. And so that's used in a few steps here. After manipulating this in there are various manipulations I won't go through, but at the end of the day, you get an inequality that says that the integral of scalar curvature squared over 24 is bigger than the integral of W plus squared, plus a term involving the size of the covariant derivative of omega. And of course, this term will vanish exactly in the Kähler case. So we get that statement, first statement about balance. By contrast, the statement I made about positive scalar curvature is basically a triviality. You just again look at that statement about, and this is actually sort of parallel to one of Matt's arguments. So but here you're in an almost Kähler case, you have this very simple relationship between a component of Weyl and the scalar curvature. In particular, you have an inequality between a component of Weyl and the scalar curvature. And so using that, and now assuming the scalar curvature is positive, you apply Cauchy-Schwarz, you get this inequality. And then you only get equality in the case when you're on a Kähler manifold. All right, so that's the last result I thought I would tell you about. The main point is I think that this question of balance between scalar curvature and Weyl is a good general theme, and I think that one can learn a lot of things about four-dimensional geometry by studying it. Allora, infine vorrei ringraziare il Centro Ennio di Giorgi per avermi invitato. Che piacere tornare a Pisa. Grazie. Thanks.
Time for questions. Is there some questions?
Could you go back to the slide with the statement? I just wanted to make sure. I don't think I quite understood this.
This last there?
Yeah. So we say so if mg omega instead has scalar curvature s greater than or equal to 0. So instead of what?
So in the first, these have different hypotheses. The
Right.
first conclusion depends on assuming that you have a harmonic self-dual Weyl.
Okay. All right. So
If you drop that and
Okay.
instead assume the scalar curvature is positive, you get the opposite inequality.
Okay.
And so the whole point is that it's not as if you get an inequality in one direction or the other automatically for all almost scalar metrics. There are interesting classes of almost scalar metrics where the inequality will go one way or the other. And so if you have both of those hypotheses, then if it's both, if you both have harmonic self-dual Weyl and if the scalar curvature is non-negative, then in fact you're looking at a constant scalar curvature Kähler manifold.
Okay.
So by the way, I mentioned the so-called Goldberg conjecture and Sekigawa's result on it. one reason I wanted to write this up is this is a generalization of that result, where you can clearly see that if you don't assume the scalar curvature is positive, it's false. Okay, so if you look at things that have let's say harmonic self-dual Weyl curvature are almost scalar, but where the scalar curvature is not required to be greater than or equal to 0, you can definitely find examples that are not scalar. So this does not actually give a counterexample. So what are the dumb examples? Well, consider those where you can look at anti-self-dual and almost scalar manifolds where W plus is identically 0. Certainly the hypothesis is fulfilled. You can show, though, that there's a huge world of almost scalar anti-self-dual metrics where the scalar curvature is generally negative, is negative, strictly negative at most points, and it's just 0 at a few. Then and for those, they're certainly not scalar. My suspicion is that the Goldberg conjecture is false in the negative Einstein constant range. And this is something in the direction of saying, well, yeah, okay, positive scalar curvature is going to give you a kind of control that you cannot expect in the general case. But the Goldberg conjecture remains open, and I just wouldn't, I really wouldn't encourage young, serious mathematicians to go beat their heads against it. I mean, it's one of those things where if you stumble on an idea and you suddenly see why it's true or false, great. But there are so many people that have wasted their careers working on this problem. And so this is just maybe a cautionary tale.
Is there other questions? So I have one. You said that the space of almost scalar metrics are open. Is there some topology on those sets? Numbers of connected components?
That's a very good question. I think it should be possible to give many examples where it's highly disconnected. The reason is that, for example, you can find certainly among complex surfaces, you can look at the Kähler metrics. You can find I think you should be able to find many examples. There certainly are examples of complex surfaces which are diffeomorphic but not deformation equivalent. Right? So those give you examples where they're definitely thinking about just the Riemannian geometry, where the Kähler metrics sit among Riemannian metrics. That will be disconnected in some examples. The question is, can you push that further? Now, if you take those connected components of the Kähler metrics and think of them in the almost Kähler metrics, are they still disconnected? And I don't know, but it seems to me there's a good shot. Now, that's a great question. I don't know. I don't know the answer. It's a stimulating question.
Yeah, you showed us that in the first lecture, I think that you can classify back-flat metrics which are scalar. So do you think in the almost scalar case, not in the negative scalar curvature case, as you were saying about self-dual, because it would be impossible, but maybe in the non-negative, so when you have non-negative scalar curvature and back-flat almost scalar, you think it would be possible to get the classification or something like that?
Yeah, so I think that's a good question. So if you assume that you have a symplectic four manifold and that it has a positive scalar curvature metric on it, you could, in particular, you could look at the almost scalar metrics, but you could also just say, suppose there is some positive scalar curvature Riemannian metric on your symplectic manifold, maybe one that doesn't like the symplectic form. Total stranger to the symplectic form. That already puts strong constraints on what your manifold is. You would already know that it's diffeomorphic to a rational or ruled complex surface. That's an amazing result. It was follows from work of Macduff, Lalonde, Ota, Ono. It'd be hard to list how many people are involved, but it's lots and lots of pieces. But there's some very beautiful symplectic geometry there where it turns out that because those are manifolds where the naively defined Seiberg-Whitman variant will vanish, it puts very strong constraints on the symplectomorphism type, and in particular, you know what the diffeo type is. They're actually deformation equivalent to Kähler surfaces among the ones that have positive scalar curvature, Kähler metrics. All right, so that's a start. So you already know something about the diffeo type of what you're looking at, but it's trying to now understand what are the Bach-Flat metrics on that. Well, you have to make sure you have something to hold on to, and I don't have a. So for particular classes, like for example, if you were to ask which of those have anti-self-dual metrics on them, we have a very good answer. Okay, so the ones that admit almost Kähler anti-self-dual metrics are the same as the ones that admit Kähler anti-self-dual metrics. So we know many things. That problem is not completely finished. Of course, those are kind of the ones I've just referred to. The ones that have anti-self-dual metrics don't overlap with the ones that admit Einstein metrics, the Del Pezzo surfaces I've been discussing today. So there are lots. There are big classes of these up to modulo blowing up. We sort of know, yeah, most of them have Bach-Flat metrics. One of the mysteries, though, about the Bach-Flat condition, or even the anti-self-dual condition. Anti-self-duality, we have many constructions of anti-self-dual metrics. We know a lot of four manifolds admit anti-self-dual metrics. There's in fact, a theorem of Taub's that you could take any four manifold and blow up enough points, and you would eventually get an anti-self-dual metric on it. But my own work was sort of was more concrete and effective. You can just actually show specific four manifolds admit anti-self-dual metrics. We have lots of existence results. It's not so easy to get obstructions. If you put in an extra condition, if the metric is also almost Kähler, or if the conformal classes of what I call symplectic type today, there are very strong obstructions, and then you can kind of say what are the possibilities. But in general, if the kinds of obstructions to anti-self-dual metrics we have available right now are very crude. It's like I told you about why there's no anti-self-dual metric on S2 times S2. And that's actually a slightly delicate case. It's a boundary case. If the signature had the wrong sign, you couldn't have an anti-self-dual metric. If it's 0, then it's constrained in a heavy way. But in general, we just don't know what the obstructions are. And that's a great problem. I mean, general problem, find new obstructions to the existence of anti-self-dual metrics. There probably are some, but we're just ignorant about this.
Is there other questions? No, so we thanks Claude again for.
I would really like to thank you all for persevering through the technological difficulties, and I think my advice about such things is, if you ever, as a speaker, find yourself in this situation, just try to laugh. It's not always easy, but anyway, just try to laugh.
Thanks a lot to Andrea, Giovanni, and to all of you. it was actually quite shocking to be reminded of how nice it's a 3D conference after 2 years of gather town Moodle and the breakout rooms. So, and not just for the pappardelle, but so, which is a nice plus. Anyway, so, okay, so what I want to present today to you, it's a new kind of new existence theorems for constant scalar curvature Kähler metrics. Now, after Claude's series of lectures, we also learned a lot about how they could be useful for other, to explore the purely Riemannian situation, but I will stick to the Kähler case on this thing. And the original part of this presentation is joint work with Alberto della Vedova in Milan and Yalong Shi in Nanjing. So, okay, well, at the end of the week, this slide is almost offensive, but let me just say, our dream is to have a slide like this in every dimension. So my manifolds will always be compact. So kind of characterizing as much as possible the positive scalar, curvature, zero curvature, and negative curvature case. I should say this should be thought as kind of the first slide of 2 when going back to dimension 1, in the sense that part of the interest, everything is so interesting also in that, but there would be one of the reasons to study this kind of problems also because once you get them, you can actually start studying also what are called moduli spaces. You can start to deform them and actually study, for example, the very well-known problem of Teichmüller theory and algebraic compactification of moduli of curves. So, and that's actually part of what we are trying to do in higher dimension, but I will stick to the purely existence problem on a fixed manifold. Now, a reminder, after all these lectures, not much is left, to convince you that constant scalar curvature Kähler metrics actually do exist, but sometimes not. So where do we see that there is some problem? Well, there is a classical abstraction by Matsushima Leknerovitz about the structure of the automorphisms group of such a manifold. I'll skip that, but let me at least remind you a more recent and in some sense more heavy abstraction to the existence problem. At the beginning of the 80s, Futaki noticed that if you give me a compact manifold and a holomorphic vector field on it, and so if you take any Kähler metric in the Kähler class that you are studying, you can actually build a number in this curious way. So you take the scalar curvature of this metric, you take out the average in such a way that this becomes the Laplacian of something. And in my notation, it's H. And then you actually act on this function H with the holomorphic, a vector field, of course, differentiate functions, and you integrate over the manifold. Now, this looks a little bit like a kind of a strange game. Actually, it is actually deeply related to the second name of this conference, energy functions, but I won't touch this, how he came up with this idea. What I'm interested here is to make you notice immediately the easiest part of the story is that, of course, if by incredible luck, you started with a metric G, which was of constant scalar curvature, of course, H would be a constant, and of course, X of H would be 0, and so you would get 0. Now, the delicate part of the story for Futaki was to prove that actually this number does not depend on G, but only on the Kähler class. So if you change the Kähler class, the metric inside the same Kähler class, which actually I remind you, I will use it over and over. You can do that by the Didi-bar lemma with a function. So you take a fixed metric and then you add the Didi-bar of a function, and then you have all possible Kähler metrics in the same Kähler class. That actually this number does not depend on the representative of the Kähler class that you are using. And this is an incredibly important and useful property. Now, about 20 years after that, Donaldson revised completely this story and actually came out with a little miracle. Actually, it's not the hardest thing that Donaldson proved in this story, but at least it is very surprising. He generalized completely this the picture by Futaki, first of all, by taking not just a manifold by a scheme, okay, that you can think of it as a wild generalization. instead of while the holomorphic vector fields gets replaced by a one parameter subgroup of the automorphic group. Okay, that's another wild generalization. And then what you do is that once you have an action, you take this one parameter subgroup, you go and see how this one parameter group acts on the top wedge power of the space of holomorphic section of a line bundle. Actually, of course, there is a slight restriction. That's a Keller class. This is the Keller class we are looking here is the functional class of this line bundle. Now, not always, of course, this happens, but let's say this happens very often. It's called the polarized case, the algebraic case. So by looking at the action of the, you will get to essentially, you get the weight of this action. And at the same time, you have another invariant, of course, which is the number of holomorphic sections of this line bundle, the H0. And the idea is to take powers of this line bundle. So you are looking at this class and you take all its multiples, okay? And then you go and see as the multiple grows, how these numbers change. And kind of equivariant Riemann rock, this is a classical thing, it tells you immediately that you actually, you can expand, you have an asymptotic expansions of these numbers as the power grows, which gives rise to few coefficients that mixed in this kind of little miraculous way, give rise to a number that Donaldson proved to be the Futaki invariant every time all this picture reduces to that one. So every time the scheme is a manifold, every time the one parameter group is a holomorphic vector field, and so on. Now, this is a little miracle for me, I mean, in the sense that actually this switches completely the easy and the difficult part about Futaki. So easy was for Futaki to prove that if you have a constant scalar curvature metric, this is 0. And now there is absolutely no reason looking at this number to believe that this should be true. Difficult for Futaki was to prove that it does not depend on the Keller class. It does not depend on the representative of the Keller class, but only on the Keller class of the metric. While actually Donaldson didn't even write a metric, okay? Of course, everything here depends only on the class C1 of L, okay? So it is completely dual. So in any case, you believe the theorem of Donaldson, of course, they are the same, and then you get these numbers. Now, the point is, of course, that if you give me a random Keller manifold, by the way, sorry, I understand maybe Keller is already not too familiar at the end of the week, yes, but pick any algebraic manifold, okay? You lose something, but not too much for this talk. So pick an algebraic manifold and compute the Futaki invariant for a given Keller class. Most of the time you get non-zero, okay? So that tells you that constant scalar curvature Keller metrics are in some sense rare. So what can you do? Well, of course, you try to ask a good question to a PDE friend. So you write down what kind of equation it is. So you start with any metric, omega 0, and you want to find the deformation in the same Keller class, which actually solves your favorite equation. You write it down locally in terms of some coordinate system, holomorphic coordinate systems, and then you realize it's essentially hopeless. Okay, it's really a horrible equation. It escapes almost all the techniques that we can use right away to actually start to solve it. On the other hand, what is interesting still by looking at the equation itself is what does it happen when you linearize it. So the linearization of this equation, what does it mean? You take a family, you take the derivative of the scalar curvature at equal to 0, and you go and see what it happens. And what does it happen is that you get the bi-Laplacian plus, or I mean, these are conventions, the contraction of the Ricci form with the Didi-Bar operator applied to the function that you are using. Now, this, of course, is significantly more difficult. Notice that, of course, as a special, I will use always as a special case of the constant scalar curvature Keller problem, the Keller-Einstein problem. Of course, Einstein is more. In that case, you are prescribing Ricci, and if you linearize Ricci, remember that you are essentially getting the Laplacian. So So that tells you the jump in difficulty also at the linear level, but still, actually, I believe Matsushima himself, or Liknerovitz, or both, I don't remember now exactly, but it has a classical observation that actually you can study at least the kernel of this operator. At least actually here there is a slight misprint, because what this sentence is true only if omega 0 is of constant scalar curvature. So if you take a constant scalar curvature metric, the kernel, yeah. It's a never-ending source of, but at least at the constant scalar curvature metric, the linearization, the kernel of the linearization actually has a beautiful interpretation, geometric interpretation. Is actually the space of functions which generates holomorphic vector fields by a standard procedure. Basically, take the 1-0 part of the gradient of the function. Okay. In the Einstein case. Okay. Yeah. So notice, of course, in general, you would dream a situation where the linearization, for example, is injective and then surjective and other things. So notice that actually, again, the Futaki invariant was the first appearance. Second appearance here, of course, you would prefer the kernel to be 0. And holomorphic vector fields are always there to bother you, okay? Which is, for a geometry, is kind of strange, no? Because you think symmetries should help. Actually, here, symmetries, every time there is continuous families of symmetries, the problem becomes harder and harder, okay? Anyway, the moral is that out of this, I have to be quick, otherwise, out of this, basically, you get very, very few existence theorems genuinely, in the sense of give me a manifold and tell me, is it constant scalar curvature or not? On the other hand, these kind of properties are very good in order to study deformation theory, which is something Claude and Simanka implemented about 20 years ago in the smooth case, and it's kind of the moral of also other works in the singular perturbation methods. But in any case, so the equation doesn't work. So what else can we do? Well, energy functionals was the subject. What is there a nice functional that we can use associated to the constant scalar curvature Kähler problem? Well, actually, of course, we are in Pisa. Remember, Leonida is watching us. So, but it actually, no, it's also a little tribute to, I mean, it actually, that's the winning idea. I can anticipate, I mean, in some sense. The variational approach is much more efficient for this problem than the purely PDE one. So what does it mean? Well, of course, I mean, first problem, there are many functionals whose critical points are constant scalar curvature metrics. In this picture, and the picture I'm going to tell you about, the winning choice is what is a famous functional which was defined by Bambucci in the 80s. It's called the K energy. Unfortunately, it looked very unfriendly. I agree with you. If in this moment you are a bit discouraged, you cannot imagine how discouraged I was, but but still, it is. But there is nothing to say. It is the right functional. If you especially think of this problem from also a symplectic point of view, or this kind of more stability type of properties, this is essentially the Kempfness functional over an infinite dimensional space. So you have to work with that. Oh, sorry, and one feature, sorry, I should have mentioned one feature about the Kähler constant scalar curvature problem, which is different from the other that we have seen this week, is that actually right away from the beginning of the problem, you know which will be the constant. So if you ask me, if you give me a manifold in the class, if there is a constant scalar curvature metric, I know immediately which constant should I look for. So the question is not whether it's positive, negative, 0, okay? It's a topological quantity, which is given by this number here. It's the first class times the class where you're looking divided by the volume. Times 4 pi. And, okay, so in fact, actually, the definition is ugly, but actually the definition, it comes from the first variation. I mean, you impose that the first variation is what you want. And then you go back to check what should the functional be. Now, so what would be the variational approach tell you? Okay, is this function coercive in the language more classical language? Meaning, if the domain of the function, of the functional, has some kind of distance function, or something that mimic a distance function, is it true that if the distance goes to infinity, the functional grows at least like the distance? Okay, so you can imagine some kind of it's a kind of convexity property that should guarantee, at least intuitively at the beginning, that a critical point exists. Now, this has taken more than 20 years to put every piece together. So what I called here the dream theorem, because actually, as I said, there are many competitor functionals, there are many competitor distances, and so on. This was an extremely complicated story, beautiful, but I mean, at the end, now, thanks to, and by now I really mean 3 years ago, we can actually state a theorem which closes at least the conceptual picture. So there exists a constant scalar curvature metric if and only if this functional is proper, which is, I don't know exactly why in this word has become the language for coercive. Yeah, but it's proper on the space of potential. The domain, I will come back to this point because I'm ignoring a crucial point. Okay, then I'm not ignoring anymore now. I'm taking only C infinity functions, okay, because I'm interested in smooth metrics. Yet the space of C infinity function is largely incomplete. So in fact, actually what took many years to understand is which is the best completion of the space of C infinity function suitable for this kind of problems. And I want and have to mention right away the names of Darvas, Berman, and Chang. Okay, they were. Okay, this theorem was proved for the Keller-Einstein problem by Tian without automorphism, by Darvas-Rubinstein for Keller-Einstein with automorphism, so with holomorphic vector fields. And then Berman, Darvas, and Liu proved one implication. And then, as I said, this Chang actually means a sequence of works that will come up every 5 minutes in my talk. So in one of their papers, they also fill the missing arrow of this theorem. So at least conceptually, we are there. We have a functional, and if we manage to prove coercitivity of this functional, we are done. Now, can we? Okay, the moral, I think I've already said. So can we? There are a number of people, first of all, myself, trying to see whether all these conditions are actually in practice useful. Okay, this is all beautifully conceptual, but I mean, at the end of the day, you meet your friend, gives you a manifold and say, okay, is it Keller-Einstein? Is it constant scalar curvature? And you say, ah, well, it's enough to check that the K energy is proper. That's not exactly a good answer, okay? So in general, I guess the answer, I think we all agree, the answer would be hopeless. I mean, we don't know how to check the properness of these kind of functionals, but we can be a bit more humble. So ask which geometric constructions preserve properness, okay? So, and that's the topic of today. And this is the situation which I want to describe to you. So the situation is I mean, for me, it's probably the simplest possible geometric operation. You take a base manifold where you suppose you know everything. Here it's called N. So for example, you know that you have a solution to your problem, and you take a cover. Now, you take a cover and you ask yourself, well, does the cover have a constant scalar curvature metric? Well, at least in the pullback class, okay? This has appeared already as a source of example. This, well, sorry, just a second. I don't want anybody to be scared by the algebraic language. So Galois cover just means that you take the quotient and you get the base. Okay, so you have group action, you quotient and you get the base. Now, if the cover was a cover in the sense of geometry 2 in Italy, so non-ramified, the problem would be completely trivial. You take the base metric, you pull it back. Of course, this would not be the picture by what Claude is hinting. I mean, you cannot have a cover of surface of genus 3 over the sphere. But I mean, suppose for a moment you put another sphere there, you pull back the metric, and that's it. Now, so the question, of course, the interesting question arises every time you have branched locus, okay, ramification. Now, in that case, what's happening? So what if you do the triviality? Take the constant scalar curvature metric and pull it back. Well, this becomes highly degenerate. And it becomes highly degenerate along the ramification device. Okay. So the question, in fact, you could phrase it, is it a useful information or not? I mean, I give you a manifold and I give you a highly degenerate metric of constant scalar curvature wherever it makes sense outside the ramification. But can you actually use it to prove the existence of a smooth one? Okay. Okay, this, of course, is not, we are not the first one to study this question. The Keller-Einstein problem, I think I have to accelerate a little bit. The Keller-Einstein version of this story started by Tian, and I'm studying this problem explicitly thinking of the variational method. So now I rephrase the question. Suppose that on the base, the functional is proper. Can I actually prove that the functional is proper above? So this idea started with Tian with another functional, but in the Keller-Einstein case, we did some work with Giuggi and Pirola. In the Keller-Einstein case, it's important to quote this work by Chili and Sonsun. So they actually proved, they gave essentially almost our condition, but we are exactly in the same situation, but so there is a ghost in the room. I told you, if you take a smooth metric below, you pull it back, becomes degenerate. So you might ask, what should I do below in order to have a smooth metric above? And the answer, if the ramification locus is not bad, irreducible, smooth, and so on, actually the answer is easy. The answer is that if you can produce below a conical constant scalar curvature or conical Keller-Einstein metric, then actually if you pull it back, it becomes smooth. Of course, if the angle is related by the order of the group. So the group actually opens the angle, and if the two things are compatible, you actually get smoothness, okay? And that's actually the idea of Lee and Sun. But since they insisted on, I mean, they used conical metrics, they had to assume that the ramification, well, actually, D is the branch locus in this notation. The branch locus has to be smooth and irreducible, because for non-smooth and non-irreducible, you don't really even know what a conical metric is. Okay, so the problem is, it's already quite complicated if, so there are various hierarchies of bad singularities. So if in a picture, if the branch locus is smooth and irreducible, you know what it means to be conical. If it's a simple normal crossing, which is what algebraic geometry would say about this picture, you can do it. It's a bit painful because really what it means for the angle, you have two at the crossing points, but you can still make it work. But I can tell you there is absolutely no way you can make sense of a conical thing on something like that, okay? So it's a great idea, but it has this kind of limitation. At the same time, I mentioned already this sequence of papers by Chen, which actually I think they really changed the problem probably forever. They actually, the sequence of paper, one is called existence result. They actually proved an existence result about, in general, not in the case of Galois covers. I mean, give me a manifold, does it exist a constant scalar curvature metric? And they actually proved, what I'm interested in is part one. I just didn't want to cut it because the sentence was, if one of the following holds, and then if there was only one. But really what is important now today is number one. So they have a topological condition plus some analytical conditions. You can see, I won't even define what is alpha and so on. But let me translate it automatically in the case of Galois cover. So I take Chang and I translate it here. So in this situation, if M is actually the cover of something, what they are really saying is that there are two special line bundles over this manifold M, that if there are two special line bundles, and one is the canonical plus B, and the other is this peculiar combination again of the Keller class and well, sorry, I'm calling them line bundles, but this is actually a Keller genuinely, I mean, sometimes it's not a polarized. So, but if these two classes are NEF in the language of algebraic geometry, then what they actually conclude is that the manifold has in that class a constant scalar curvature method. Now, just one second, what does it mean NEF? NEF is a way to close the ample cone, okay? So ample classes are those which are positive. NEF means that these are the classes, the line bundles, for example, if they were line bundles, you could say these are the line bundles that if you restrict them on a curve, it has no negative degree. It's a definition that tells me, for example, almost nothing, but then fortunately Kleinman proved a beautiful criterion saying a class is NEF if and only if, essentially, every time you add, even infinitesimally, epsilon ample, so if you take L plus epsilon A, so L is NEF if every time you do something like this, you get ample. Ample means it has a metric of positive curvature, okay? So every time you insert a little bit of positivity, you actually, the globally becomes positive. Probably it's for us, it's more friendly, a beautiful famous theorem by Demailly, Peternel, and Schneider, which actually is kind of the metric version of Kleinman, because it says that something is NEF if and only if it has an Hermitian metric whose curvature is greater than or equal to minus epsilon curvature, minus epsilon omega, for every epsilon, which in some sense it's kind of similar. It's the metric version of this. So it could be negative, but it has to be negative at every epsilon, okay? And every time you add a little bit. In any case, it's something algebraic geometers know how to control in practice on examples. So this is Chang. So what have we proved? Okay, we gave a new sufficient condition, which actually looks not too different from Chang. I just point you where the difference is. So B will be the ramification divisor below. And basically Chang is exactly the same thing. So notice that we are asking Kn plus B delta, there is this delta, okay? So Chang is delta equal to 1, okay? Now we allow a parameter, so there is a parameter that we allow to be bigger, and then the condition remains the same. So these two classes has to be NEF, okay? Now, so of course, this raises immediately the question whether having this parameter free is meaningful or not. It actually adds something. Just one word about the notations. You might notice, what is B? Typically, I mean, at least in our understanding, if every time you have this situation, you would think of B as the branch locus and R to be the ramification divisor. Now, in order to have a nice Riemann-Hurwitz formula, algebraic geometers have decided to put numbers, I mean, coefficients on this divisor. So it's not just the set. It's a set with some weight, and this number 1 or -1 over D is nothing. is nothing, but it's just to make the Riemann-Hurwitz formula look great. So you want to know what is the canonical bundle above with respect to the canonical bundle below. And then, of course, this is a condition about the ramification and branch locus. And in order to have it the simplest possible, you put these numbers here, okay? So this is just a convention. If you prefer to think geometrically as B as the set with every point with multiplicity 1, then unfortunately the Riemann-Hurwitz formula becomes a mess, and then everything becomes more complicated to state. Okay, you can rephrase it. Notice I still have not put any condition about what kind of Galois of cover I'm studying. Of course, keep in mind that there are a hierarchy of difficulty. The simplest ramified covers will be the cyclic ones, then the abelian ones, and then the general ones. Okay, so of course you can play the game of simplifying the statements for every step. Okay, I think this I've already discussed. So this generalizes Lie soon in the sense that now the ramification divisor can be, the branch locus can be whatever it wants, and generalizes Chen in the sense that there is this now space for moving, but I still have not convinced you that this is interesting. So let's, before telling you a little bit about the proof, can we actually now play the game that we wanted at the beginning? So, and actually this turns out to be very flexible. So start with the simplest constant scalar curvature metric you can think of, for example, Pn. And now, in fact, actually in this case, I'm looking directly for cyclic covers, so the simplest ones. Now I impose the branch locus to be a multiple of the hyperplane section. I don't really care about the set. I really care about the class, okay? So it doesn't really matter. You can even take a hyperplane and count it 60 times, okay? Or you can take a smooth object in that class. For that theorem, for our theorem, it doesn't make any difference. Of course, the manifold will be different above. But then, can we actually check whether these two famous classes are Neff or not? And actually, it turns out that there is a significant difference between us and Chang. Basically, what at the end of the story, we are basically requiring that this lambda is greater or equal to n+1, while Chang would have required this. Okay, it looks not too much, but there is already in the cyclic and with base space Pn, there is already a lot of space for. Now, let me list a few curiosities because everything here is highly expected, but just to mention, for example, these curiosities are very well seen if you take as a base manifold P1 cross P1 with two copies of the, well, with what? With actually, we leave free the parameters of which size the two spheres will have, A1 and A2. And we also have another two parameters coming from where do you want to put the branch locus, okay? And this will be this B1, B2. Just, okay, you can go and check when a cover of cyclic cover of some degree will have, that's okay. But what I want to now notice is that which scalar curvature am I getting upstairs, okay? And the scalar curvature, it's simple. As I said, the scalar curvature is a cohomological number. So you just count and you get this formula. So maybe I found it a bit curious, so I just wanted to tell you. Of course, below it's positive. Above tends to be negative. Could actually be zero, could be also a little bit positive, but in general, this game of Galois covers reduces the scalar curvature, okay? Another, this is completely expected. I mean, even in the case of Riemann surfaces, of course. But what I never appreciated actually is this final thing. There are actually many situations where you can actually construct Keller-Einstein metrics on top, coming from constant scalar curvature, non-Keller-Einstein metrics below. Honestly, I did not expect this to happen, but it does, okay? So there are, so this theorem actually gives also new Einstein metrics, because every time us, Lee, Soon, and so on, we always assume the existence of an Einstein metric below. Now, in this situation, constant scalar curvature metric actually generate Einstein metrics above. Okay, now that's for cyclic. Now, the general abelian, the general theory for abelian Galois covers actually has been developed again here in Pisa by Rita Pardini. It's a beautiful, but I mean, rather technical story, so I won't enter it. Let me just mention as a kind of philosophical fact, you could actually think of, in general, of an abelian cover as a composition of cyclic. So in some sense, you could actually reduce everything to step by step. It's not exactly the right thing to do, but I mean, because it's more interesting the non-abelian case. Now, actually, sorry, I should have said, what am I doing now? Because you see, I told you, pick a Galois cover and ask yourself, can you actually lift the constant scalar curvature problem from one to the other? Right, there is a big problem. Do Galois covers exist? Because otherwise that would be a fantastic way to spend our time during lockdown. I mean, you prove a theorem. So, and actually, I should probably stop now for a moment, because this has, I actually thought Hurwitz knew it. I was very naive. So I studied the constant scalar curvature problem, and then I realized that actually it was largely subject of current research. So for cyclic covers, this is classical. This is probably Hurwitz knew. You can actually assign, so if you give me a manifold, you can even, and you want a cyclic group, you want to construct a Galois cover with a given cyclic group, you can even assign the branch locus. It's very simple. It's a very general, elegant construction. But as soon as the group is non-cyclic, this fails, collapses. This construction collapses, and you have to ask yourself, do they exist or not? And am I free to assign the branch locus, or maybe sometimes they exist, but only with very special ones? That's what Pardini did in the abelian case. In the non-abelian case, the situation is even more messy. For example, we have taken as a prototype case the dihedral group, of course, of order at least 6, in order not to be of the previous types. And the question was, okay, if I give you a manifold and I want D3 Galois cover, do they exist or not? So for example, this has been solved by Catanese and Perroni only a few years ago. And okay, the answer is a little bit technical. Okay, the answer, it is a little bit technical in the sense of the language of algebraic geometry, but it's very elegant and it's actually not hard. The point is that, of course, you cannot assign the branch locus as you want. And you cannot always do it, but many times you can do it. For example, I should say, I didn't catch it, but for example, you can even construct a Ricci flat metric with K3 surfaces with this game. So for example, if you take, I don't know whether this is completely well known, but if you take P2 and you impose a sextic branch locus, D3 works. You can actually cover P2 over a sextic with a D3 symmetry. And but then you realize you can just go and compute what kind of manifold that you construct, and you have constructed a K3 surface. So that means the constant scalar curvature metric has to be Ricci flat. Okay. Okay, so we take Catanese Perroni, we check what is it saying for, again, for Pn and the hyperplane, multiples of the hyperplane line bundle and so on. It turns out that there are millions of examples. Now, okay, maybe I should spend a few minutes about telling you how is it proved, but I think the moral is, well, we had fun. We constructed an incredible amount of unexpected amount of number of constant scalar curvature manifolds with Kähler classes and so on. Now, of course, the question is, among all these examples, maybe is there anything a bit more interesting than others? And for that, I think that the real question would be to connect it to the general picture now. I think that the game of producing examples is to test the general theory. Now, in this world, the biggest problem is what is called the Tian-Yau-Donaldson conjecture, which asks, predicts that such a metric exists if and only if the manifold is K-stable, for example. So for the Keller-Einstein problem, you see, we had the very neat conditions about the Keller-Einstein problem. Say conditions below, something like here, in the spirit of my work with Gyugno and Pirola or Lee and Sun, where you could say Einstein below, Einstein above. So if you knew a little bit about this big conjecture, you could ask, is K stable below, K stable above? Does it give the same condition? And the answer is yes. Dervan actually proved it. And it turns out under exactly the same condition. So the metric, and after all, in the Keller-Einstein case, we know that the conjecture is true. So that means actually here, these theorems are not improvable in this respect, okay? But in the constant scalar curvature situation, we don't know the answer to the big conjecture. So I think it would be nice to check if among these conditions are actually exactly those which preserve the lifting of the K stability, which is a much more sophisticated thing to check, okay? I think that would be kind of a natural next step. Once you have. Another, maybe all my moral was, it is a very flexible construction. So let me anticipate a question. Is it even can you even hope to get any possible M? Because you say, are you driving in the direction of proving that every manifold has a constant scalar curvature metric? Well, no. So here I want to say a warning, not every manifold for sure is the Galois cover of something. Its automorphism group has to be a bit special, okay? So it is still a very flexible thing. You would expect, I would say, almost the generic manifold to have this kind of structure in some form, but not everything will be of this form, okay? So in the last, I think I can even probably, let me give you an idea of how to prove this kind of theorems, because that's really the variational method in action. Right, okay, if you want to have fun, you can, you see, I still, all the examples I gave you, the base space was actually the projective space. Okay, but fortunately, we know something else. So for example, you could put blow-ups of P2 below, and there actually it gets fun because you can put, for example, a Keller-Einstein metric, the famous CU metric that Claude has used also. But you can actually go very far from there with the blow-up argument we proved with Frank Paccard. So there are two, basically there is this, the central metric, and in the boundary of the Keller cone, there are these tiny exceptional divisors, and you could play the game putting both as base space and see what does it happen when to lift them. And okay, this becomes, when I said millions and millions, here you can start doing whatever you want, essentially. The conditions, as I said, this Neff properties is very mild. So that's really the moral of the story. Now, but how do you prove something like this? Well, the strategy of the proof is the obvious one. So what does it mean, the obvious one? You suppose you know everything below. Suppose you know everything means you have a constant scalar curvature metric. In fact, actually, we need less. You need only bounded from below for the functional. But actually, this is now a commonplace. But it's a difficult commonplace every time you have to check. But this actually implies that what is called the log K energy is proper again. So what is the log K energy? It's difficult to explain, and the formula become completely irrational. But the only thing where the situation where you can actually grasp a little bit the geometric meaning, the log K energy would be kind of the natural functional, again, in the sense of Mabuchi, which will tell you whether a conical, if you are prescribing a smooth, irreducible divisor as your possible source of singularities, then the log K energy is that thing that should be proper if you have a conical solution to your problem. Okay. So, and this actually is part of the, so the idea is that if you have a smooth metric, and if you, now I'm restricting myself to the smooth irreducible, otherwise I cannot draw a picture, but if you prescribe a possible singular set, then actually if you have a smooth one, you can actually produce a conical one, essentially of every angle. And this is a circle of idea that actually Donaldson has introduced about 20 years ago, 15, 20 years ago, which actually led to the solution in the Keller-Einstein case. But it was actually, in that situation, of course, the problem was the opposite. I mean, you start with conical and you want to open up the angle to make it smooth. And that was the big part of the story. Now we are in kind of in the dual situation. We have the smooth one and we want to produce the conical. Okay. And why we want to produce which is non-trivial, of course, it's much less difficult than the other part. Okay. It's non-trivial, but that's what you can do. And why do you want to produce the conical? Because I hope I convinced you at the beginning that if you have the conical, the Galois cover will actually open it up. Okay. Of course, but okay. This would all make sense, but this would be another proof of Lee Sun. I mean, our contribution was to get rid of irreducible and smooth. Okay, so, but unfortunately, I cannot give you another geometric interpretation. If the divisor is a mess, well, you formally do the same thing, even though you don't make a geometric interpretation of what you are doing. Okay, and it works. The point is that the fact that the divisor was nice and smooth and so on was not actually helping to prove this theorem. That's essentially our observation. Okay, the divisor could be horrible, and still this property would hold. I should say, yeah, there is a big regularity problem that I mentioned at the beginning. When I defined the functional, I said, look, be careful, I'm defining on the smooth functions, but actually, of course, I need to complete this space in some form. Thanks to the work of many people, Darvas, Berman, Lu, and then it is now quite clear that there is a space that now has got the name E1, which is defined in this way, which is a completion with a suitable distance on the space of smooth functions, which should be the right place where to. And what does it mean, the right one? Right one means that it has the following two properties. That actually checking properness over this space actually comes from checking on the space of smooth potential. This is, of course, something that tells you already that this should be a good completion. And the other one, well, okay, that's what we have to prove in order to prove our theorem. But actually, the other one is really a key breakthrough in the story by Chang. So the regularity of solutions. So if you have a solution in this space, Chang actually proved is actually smooth. So we had to revisit their proof in the G invariant case, but honestly, that's not really the heart of our problem because G is only a discrete group. I mean, this revisitation are by far non-revisitation if the group has continuous parts. Okay, honestly, it's something you have to do if you have to write a paper. You have to go through all the steps and say, this works, this works, this works, and or you make a phone call to Giuggi and say, Giuggi, sorry. But it's just a check that a discrete group does not kill the proof of the irregularity theorem. Okay. So with all these ingredients, then you just, but you need to prove that lemma. And that lemma is the key one because it's telling you, you see here on top, we are relating the log K energy below to the K energy above. So if one is proper, the other is proper, okay? Notice that the K energy above is constructed with the degenerate metric. That's also part of the interest of this story, okay? And I think in this way, I'm done. Okay.
Is there some questions?
So when there is no constant scalar curvature metric, is there like a surrogate reasonable problem one can study? Can you find, can you?
Well, there are cases like extreme Taylor metrics.
Yeah, that was I was thinking. The problem is, yeah, so there is at least one famous generalization of the constant scalar curvature problem in Kähler geometry, which is the extremal one. Extremal means that the gradient, again, the symplectic gradient of the scalar curvature is a holomorphic vector field. So of course, if the scalar curvature is constant, this is zero. And so, and this is related to the critical point of the Calabi function. I mean, these are the critical points of, now, yeah, in principle, you can certainly attack the same problem, whether extremal metrics lift. Yeah. I'm trying to think whether, you see, an extremal metrics have, since you have a vector field, you have a holomorphic, you have not just a metric in some sense, you have a metric and the holomorphic vector field below. I was just thinking whether you immediately have to impose some kind of compatibility between the Galois cover and the holomorphic vector field that you have below. Probably not. But this is certainly. Exactly. So presumably the only conjecture you could make is that it could still be possible that extremals in some sense give rise to constant scalar curvature. Well, that would be surprising. No, I think that's a good question. I mean, it's not impossible, but no.
Okay, thanks.
Another generalization of the problem was specifically the Kähler-Einstein methods.
Solitons, yes.
So, but I mean, that one's not for general Kähler classes. You don't really.
Right.
There's no nice formula generalization of that I know for an arbitrary Kähler class.
Thanks.
Is there other questions? So I have one. So did you know, so you have this, you know, there is a critical point that is a constant scalar curvature. Did you know where it is in the Kähler cone? Because
you mean the one below? Sorry.
Yes. Yeah. So yeah, compared to in order to understand the geometry, because these do not give you the geometry of these metrics.
Okay, probably I understand what you mean.
Does the estimate on the properness give you an idea where is this critical point?
No, where is it? No.
Say where it's definitely not.
Yeah. For instance.
No. But this would not come from analyzing the K energy. What I think would be interesting to spend a little bit of time to understand if this flexibility that is appearing is actually giving, at least in many cases, open sets of the Kähler cones. I mean, which is the degree of freedom on the Kähler class? Because actually, we always said, well, you take the pullback, you take the pullback, take the pullback. It could be that you can actually invade a bit more than, but that's not because you go and look at the properness of the K energy. It's more a geometric question whether you can.
there is no more question, we can spank.
Thank you.
I suggest that we try to connect the next speaker and go on. It's a pleasure to introduce the last speaker of this meeting, Eduardo Garcia Rio, which is going to talk about four-dimensional homogeneous critical metrics.
Okay, thank you very much. So thank you very much for the invitation. I'm really sorry that I could not travel to Pisa and to attend most of the meeting, but well, at least I will try to show you some joint work with Miguel Brozos and Sandro Cairo, and we are working on critical metrics for quadratic curvature functionals. So just in order to fix the notation, we are working with Riemannian manifolds. We denote by R the curvature tensor, the rho is the Ricci tensor, and tau is the scalar curvature. And so essentially, all this begins with the Hilbert-Einstein functional, which is perhaps the simplest curvature functional, and critical metrics when one restricts to constant volume variations are just given by the Einstein condition, so that the Ricci tensor is a scalar multiple of the metric. So if one goes one step on and consider second-order curvature invariants of the Riemannian structure, those are generated. This is a four-dimensional vector space generated by the square of the scalar curvature, the norm of the Ricci tensor, norm of the scalar of the curvature tensor, and the Laplacian of the scalar curvature. So we may consider a linear combination of these invariants, and so we have a general quadratic curvature functional. And the critical metrics for these functionals, when restricting to constant volume, have been computed by Bergers and years ago. And so first of all, I would like to, even they appear quite a number of times during this week, and at least in the lectures of this morning, there are some special cases where these invariants are relevant. So the simplest quadratic invariants are given by the L2 norm of the curvature tensor, the Ricci tensor, and the scalar curvature. And so, for example, if we compute the Weil tensor, and if one computes the L2 norm of the Weil tensor, this is just a combination of the three functionals. So this is just a special case, and the critical metrics for this functional have been widely studied, and they consist of a vanishing of the Bach tensor. So they appear quite a number of times this morning. But there are some other combinations which are also of interest. One of them is the volumal functional. So if one computes the volume of geodesic spheres in a Riemannian manifold, this volume is you may interpret the curvature as a deformation of the volume with respect to the volume in the Euclidean space. And when one considers this deformation, the quadratic part of this deformation is given by essentially this invariant plus another term which involves the Laplacian of the scalar curvature. So it is quite interesting to investigate this functional in connection to determine the geometry of a manifold in terms of the volumes of small geodesic spheres. And there is another one, which is a combination which is important for our purposes, which is the Gauss-Bonnet theorem. So if we, for this special combination of these invariants, we get a topological invariant. So all metrics are critical in dimension 4 for this functional, and this gives us a universal curvature identity. So as well as any metric in dimension 2, the Ricci tensor is a multiple of the metric. We have a corresponding curvature identity in dimension 4, which comes from the critical metrics, or from the from the gradient of this functional here. So if one specializes the situation in the simplest case in the dimension 3, we have that the Weil tensor vanishes. And so we have that the whole curvature tensor can be expressed in terms of the Schouten tensor. And then we'll have a relation between these second order invariants. And therefore, any quadratic curvature functional is a linear combination of this L2 norm of the scalar curvature. And we wrote it this way, a combination of the L2 norm of the Ricci tensor and the L2 norm of the scalar curvature. So where this parameter t is may take different values, which correspond to different interesting situations. So, for example, one of the cases which have been studied before is the case when we take t equal to -3/8. So this corresponds to the functional defined by the second elementary functions of the Schouten tensor. And this was investigated by Gursky and Biaklowski years ago. And one of the interesting things of this functional is that when one considers the critical metric equation, this equation is given by a symmetric tensor field, which is divergence free. And this makes this functional of special interest for people working in massive gravity theories. And they are essentially built out of this special case here. And also an important observation is that when studying this functional, the energy of the functional is, whether it is non-positive or whether it is positive, it plays an essential role in the results. And we will see that this is also the situation for other functionals. So the L2 norm of the curvature tensor, this functional is equivalent by this relation here to the functional ft corresponding to t equal to -1/4. And examples of non-Einstein critical metrics for this functional were constructed by Lamontagne in SO3. And finally, just another example, this volumal functional is indeed equivalent to the functional ft for t equal to 13/4. And we will see later on some results about this. So the critical metric equations for these functionals, as I said, were obtained by Berger many years ago. And if one restricts to metric variations with a constant volume, then these are the equations where nabla2 is the Hessian of the scalar curvature, and the Laplacian is taken as the trace of the Hessian. So it's, we have a negative eigenvalues for this choice of the Laplacian. And the critical metrics for these functionals ft are given by this expression, which is also well known, where this term here, r of rho, is just the contraction between the curvature tensor and the Ricci operator. So an easy observation now is that the Einstein metrics are S critical and ft critical for all values of t. So this means that Einstein metrics are critical for any quadratic curvature functional, and this is true in dimensions 3 and 4. So for example, in dimension 5, this is not longer true, and there are Ricci flat metrics which are not critical, for example, for the L2 norm of the curvature tensor. But in dimensions 3 and 4, which are the cases we are considering, Einstein metrics are always critical for any functional, so we always will exclude these metrics from our analysis. So there are also non-Einstein metrics which are critical for all curvature functionals. So for example, if you take the product of just say an sphere and the hyperbolic space, the two-dimensional sphere and the hyperbolic plane, this is locally conformally flat metric with vanishing scalar curvature. So it is critical for all quadratic curvature functions. But one of the main difference between these two classes of metrics is that the energy of the functionals for this matrix is always different from zero, while here we may always have a critical matrix with zero energy. So the purpose of our work is to classify non-Einstein critical metrics for quadratic curvature functionals in dimensions 3 and 4. And of course, this is quite say a naive question in general, but we are restricting to the homogeneous case. So otherwise, it seems is quite impossible to do that. So in dimension 3 or 4 in general, since we are in the homogeneous setting, the scalar curvature is constant, so this term vanishes. So the only possibility is given by this part of the equation. So either this term vanishes and then the metric is Einstein, or otherwise the scalar curvature is zero. So metrics which are asked as critical are those which are scalar flat. And for the FT critical condition, so if we look at this equation and we eliminate here these terms consisting of the Hessian and the Laplacian of the scalar curvature, so what remains is this equation here. Okay, so the three-dimensional case is quite easy to describe. And so the first observation is a result by Sekigawa that a three-dimensional homogeneous manifold is either symmetric or it is isometric to a Lie group with a left invariant metric. So this means that we are to consider these two cases, so whether the metric is symmetric or whether the situation we are in a Lie group. So the first case is an easy calculation. If you take a locally symmetric, then either the Ricci operator is a multiple of the identity and the manifold is Einstein, and then is of constant sectional curvature, or otherwise the Ricci operator has two different eigenvalues and the manifold is locally isometric to a product of this form, where N2 is a surface of constant Gauss curvature. And these metrics are always F critical for T equal to -1/2. So in this case, it's just a quick calculation to get there. So in the case of Lie groups, they split into families, the case of unimodular and non-unimodular ones. And since we are working with left invariant metrics, we work just at the Lie algebra level. And using the description of Milnor, the unimodular case can be described, there always exists an orthonormal basis where the Lie brackets are given by these expressions here. So all the geometry is codified by this λ1, λ2, λ3 by these three eigenvalues, and the corresponding Lie algebra is also determined by those eigenvalues. So it's SU2 or SR3 or SL2R if the three eigenvalues are different from zero, and then depending on their signs, they are SU2 or SO3 if all of them have the same sign, and if none of them have opposite signs, we are in a SL2R or O12, which is the Lorentzian situation. It is the Euclidean group or the Poincaré group if one of the eigenvalues is equal to zero. We are in the Heisenberg group if two of the eigenvalues are zero, and we are in the abelian situation if all of them are zero. So this gives a complete characterization in the unimodular situation. And in the non-unimodular situation, what we have is that they are semi-direct products of the abelian Lie algebra with R. So the structure is determined by a derivation of the abelian algebra. So it is indeed a linear map of R2. So here we are considering the abelian part is just determined by the E2 and E3, and E1 is acting as a derivation given by this metrics, alpha, beta, gamma, and delta. And we may always normalize and work in the homothetic class, assuming that the trace of the derivation is equal to 2. So I will show you just the result. And what I will try to do is to show you for the different values of t, which give us this quadratic functional, which are the Lie groups where one has a critical matrix for this corresponding functional. So the first situation is when we have a symmetric manifold, and we always assume that they are not Einstein. So in this case, they are critical for t equal -1/2. So in the non-unimodular case, we have this description where we are assuming that the derivation has a trace equal to 2, and then we have two possibilities. One is that the derivation is a self-adjoint map, and then we have critical metrics for any value of t between -1 and -1/3, and all of them have zero energy. On the other hand, if the determinant of the derivation is equal to 0, we have critical metrics for any value of t between -3 and -1/2. And in those cases, the energy is always strictly negative in those cases. So if we now go to the unimodular situation, the Lie group is determined by these three eigenvalues. And so we firstly consider the case when two of the eigenvalues are equal. So this corresponds to the situation where the isometry group of the homogeneous space is of dimension 4. So in that case, what we have is that we have the Heisenberg group, which is critical only for t equal -3, and has also zero energy. And then we have critical metrics for all possible values of t. So they are realized on a SU2 or SL2R, depending on the range of the parameter t. And if you look at this picture here, you see that the critical points for non-unimodular Lie groups with singular derivation are the same as the critical metrics for SL2R with two equal eigenvalues. And indeed, these two metrics are isometric among them. They are not isomorphically isometric, as they are different Lie groups, but the metrics are isometric. So we will forget about this part here in what follows. And the other possibility is that the unimodular Lie group has three different eigenvalues, because if the three eigenvalues are the same, then the metric is Einstein. So the only cases to consider is when we have two different eigenvalues or three different eigenvalues. And in this case, we may have either critical metrics on the Poincaré group, which is also called the Sol-3 geometry, where the isometry group is of dimension 3, and then there are critical metrics for values of t between these two values, and metrics for t greater or equal to this value here. And the energy of the matrix is always different from 0 in the first case here, which corresponds to natural and reductive Lie groups, and in the second case here, when we have three different eigenvalues, we may have energy positive, negative, and 0. So for instance, the energy is equal to 0 for the Poincaré group. So there are some special cases in this situation. So for example, if you think on the functional given by the L2 norm of the curvature tensor, which corresponds to t equal to -1/4. So this corresponds to this value of t here. And if you look at the picture, there is only one possible metric which is critical for this functional, which has to be realized on SO3. And this is indeed the metric constructed by Lamontagne. So there are no other homogeneous critical metrics for this functional in dimension 3. If one considers the functional given by the second symmetric elementary functions of the Schouten tensor, this functional is equivalent to the functional corresponding to -3/8. And this is it occurs here. And we have two possible critical metrics. We have a critical metric on SO3, which has been constructed by Gursky and Biaklowski, and it has positive energy. And there is also a critical metric on the non-unimodular Lie group. And in that case, it has 0 energy. And so it's quite in an opposite situation to the metrics constructed in the paper, that they show that any metric with 0 energy for the functional is locally conformally flat in the compact case. So these metrics are never, the manifold is never compact. They are diffeomorphic to R3, and the metric is critical but not locally conformally flat in this case. And if we think on the, for example, the volume functional, so the functional is equivalent to the functional given by, so here is a, yeah, this, okay, it's 13/4. And if you come here, there is only one possible critical metric for this functional, which has to be realized on SO3. So for an appropriate choice of the eigenvalues here, one has critical metric for this functional here. Okay, so the observation now is that well, there are plenty of critical metrics in the homogeneous case. So one may think about a further property of these critical metrics, and so we consider those which have zero energy. So if we think on Einstein metrics, which is the trivial situation, they are critical, for instance, with 0 energy for t equal -1/3. So this is because the square norm of the Ricci tensor minus 1 over the dimension, the square of the scalar curvature, is always equal to 0 for Einstein metrics. So this is has 0 energy, but there are other metrics which are also 0 energy. So for example, as I said before, all symmetric spaces of this form have 0 energy for t equal -1/2. In the case of the Heisenberg group, there is only one critical metric, and for t equal -3, and it has 0 energy, as well as for the Poincaré group, where for t equal to -1, one has this metric has 0 energy. In the non-unimodular case, whenever the derivation is self-adjoint, we have a critical metric for this value of t, which is -1/2, the trace of the square of the derivation over the trace of the square plus the determinant. And as I said before, all these metrics are diffeomorphic isometric to R3 with this metric. So the thing is that in all these cases, these metrics are Ricci solitons. Indeed, they are self-similar solutions for the Ricci flow. So if we consider the Ricci flow metrics which evolve by homotheties and diffeomorphisms, these are characterized by this condition here, and this holds true for all these cases. Okay, so indeed, an observation is that Lauret introduced algebraic Ricci solitons some years ago by an algebraic condition on the Lie algebra of a Lie group. So what this condition means is that when the Ricci tensor, Ricci operator is a multiple of the identity plus a derivation, so this derivation induces one parameter family of automorphisms of the Lie group. And if one considers the vector field associated to that flow, then one has that it provides a solution to the Ricci flow, in the sense that the original metric evolves by homotheties and not just by diffeomorphisms of the manifold, but for automorphisms of the Lie group. And so that is what is called an algebraic Ricci soliton. And it was shown by Romina Arroyo and Ramiro some years ago that indeed any Ricci soliton is homothetic to an algebraic Ricci soliton in low dimensions. So if dimension is, for example, 3 and 4, any soliton is homothetic to one of these. And so what we have is that a three-dimensional homogeneous manifold is critical for a quadratic curvature functional with zero energy, if and only if it's a Ricci soliton. So, for example, in this case, this is not necessarily an algebraic Ricci soliton. For example, if you take here n to be the two-dimensional sphere, this is not this symmetric space is not realized as a Lie group, but this is anyway a Ricci soliton which is critical with zero energy. So since we got this equivalence in dimension 3, we decided to have a look at the four-dimensional case. So, and indeed, if one looks at this condition, what this means is that any three-dimensional homogeneous space which satisfies this equation is a Ricci soliton. So this is probably not expected for arbitrary Ricci solitons in the non-homogeneous case, since I mean, for example, Catino and computed this expression for an arbitrary Ricci soliton, and in the general situation there are many other terms which appear, which should appear here, and those are not appearing in the three-dimensional homogeneous case. But so in the non-homogeneous situation, one expects that this equivalence is not longer true. But so if we move to the four-dimensional situation, then things become much more complicated. But at least at the very beginning, the situation is a little bit parallel to the three-dimensional case. And there is a result of Berard-Bergerie in the 80s, where he showed that a four-dimensional homogeneous Riemannian manifold then is either symmetric or isometric to a Lie group with a left invariant metric. So this is completely parallel to the result of Sekigawa, and hence one may try to see if one can do something similar. So in the locally symmetric case, the situation is again easy to describe. So either metrics are Einstein, and then they are critical for all quadratic curvature functionals, or they are products of R times n manifold of dimension 3. So this is the locally conformally flat case, and the metric is critical for t equal -1/3, which corresponds to the critical matrix of the L2 norm of the Weil tensor. So in this case, the condition is just the vanishing of the Bach tensor, or they may be products of R2 times a two-dimensional surface. So, and in this case, the metric is critical for t equal to -1/2. Of course, there are other locally symmetric manifolds in dimension 4, but they are not critical for any quadratic curvature function. Okay, so if we describe the four-dimensional Lie groups, then it is not so long list. So we have the non-solvable ones, which are direct products of SL2R or SU2 with R. And then we have the solvable cases, which can be expressed as semi-direct extensions of the Euclidean group, the Poincaré group, the Heisenberg group, and the abelian Lie group. So one can try to go one by one, and if we compute if we look at the critical metric equation, so this is now a polynomial on the components of these equations are polynomials on the structure constants. But even though the three-dimensional case was much simpler, the situation in dimension 4 is much more involved. And so we have polynomials of degree 9, and they depend on most of the cases on 6 or 7 parameters. So this means that even though they are polynomial equations, they are really difficult to solve or to understand. So this the thing is that solving this equation, one may restrict some of the variables, and we work at the homothetical class. So this is not a difficulty, but still we have too many variables, and the degree of the polynomials is still very high. So the problem is that one needs to solve this system of polynomial equations. And as you may guess, I do not want to show you any of these polynomials because this is really, really unpleasant. But it's quite an unmanageable assignment to solve. So the idea is the following, that, okay, so we have a set of polynomials on some variables. And so if we have a solution to our equations, if A is a solution of our equations, if and only if is a solution for all the equations which of the ideal generated by all the polynomials. So this is the basic observation, is quite common in algebraic geometry. And the thing is that if two sets of polynomials generate the same ideal, then the corresponding zero sets must be identical. So using this fact, the strategy is to try to obtain, say, better or simpler polynomials which belong to the ideal generated by the polynomials we have out of this equation. And if we can get such better polynomials, then one hopes to be able to solve the corresponding equation for those polynomials. And if in that case, one hopes to be able to get a complete solutions for this system, the system of equations given by this CO2 tensor. So in order to do that, what we did is to make use of Grosvenor basis, which is a basic tool in computational algebra. And I would like to show you a first result out of that. So for example, if we consider critical metrics on a SL2R times R or SU2 times R. So the description, in order to describe these metrics, we take a basis of the Lie algebra, and we specialize the basis so that B1, B2, B3 is a basis of either SL2R or SU2. So they are essentially a Milnor frame for that part of the algebra. And then since the metric, even though we have a product, the metric on the product Lie group is not necessarily the product metric. So this vector B4 is not necessarily orthogonal to this subspace. So we consider the projections of B4, different projections on that subspace. And we normalize a new vector so that we get an orthonormal basis of the Lie algebra. So when do this normalization, what we are doing is that here we have the the three-dimensional part of the Lie algebra, which is expressed in terms of a Milnor frame. And then we have some additional coefficients which came out of this normalization here. So you see the final thing is that the Lie algebra is described in terms of these 6 parameters, kappa 1, kappa 2, kappa 3, lambda 1, lambda 2, lambda 3. So if one wants to get all the critical metric for quadratic functionals on these groups, then one has to solve a system of equation on this ring of polynomials. And but in this case, the things are okay, and one can describe all the critical metrics. And this was a little bit surprise, but it is a very rigid geometry. So left invariant metric on any of these groups is critical for some quadratic curvature functional, if and only if it is locally conformally flat. So in that case corresponds to the choice of the 3 parameters, lambda 1, lambda 2, lambda 3, equal to each other. And the metric is indeed isometric to a product R times a three-dimensional manifold of constant sectional curvature. So being locally conformally flat, it is critical for t equal -1/3, and the energy in this case, so there is a mistake here. The energy is never equal to 0. So the energy is not 0. So sorry for this misprint here. But the thing is that I mean, in this situation, one can easily describe this matrix, and all of them occur in this Lie group, because these 3 eigenvalues are the same, so they have the same sign. So this is also quite different with respect to the three-dimensional case, because in the three-dimensional case, either this group SL2R or SU2, they had a critical metrics for many different choices of these parameters. So for instance, when 2 of them are equal and the third one is different, then they are always critical for some curvature functional, but they are not critical anymore when one multiplies by R and the dimension goes up. So the situation now for the other solvable Lie groups is quite more involved. And for example, if one considers these semi-direct extensions of the Poincaré or the Euclidean group, so in this case, one still we are able to give to describe all the critical metrics in these situations, and essentially they are summarized in a table like this. So here I wanted to emphasize which of these metrics are realized on semi-direct extensions of the Poincaré group, and in blue the ones who are realized on semi-direct extensions of the Euclidean group. So and essentially this value here is very close to 0. So essentially for any value of t less than 0, we have some critical metrics in this situation. And so, but okay, once we have plenty of critical metrics in this on these Lie groups, but the situation is what about the energy of this metrics? So the thing is that there is only one possibility for a metric of this to have 0 energy, which is a metric given by this expression. And in this case, it's easy to check that the Ricci tensor plus this times this multiple of the identity is a derivation of the Lie algebra, which determines an algebraic Ricci solid. So in this case, the critical metrics with 0 energy are indeed Ricci solitons as well. So the next step is the case of the Heisenberg semi-direct extensions of the Heisenberg group. And in this case, the calculations are much more difficult, or at least we were not clever enough to to solve the general situation. So we just consider the case where there's functionals with zero energy. So, and in this case, we can determine all the metrics which are critical for a quadratic functional with zero energy, and they are indeed quite a short list. So it is either, this means it's just the direct product of the Heisenberg group with R. So, or there is another family of metrics here, so which are described by a derivation of the Heisenberg group, which is a three-step nilpotent, or there is another family where we have sorry, in this case, the first one is a derivation which is diagonal, and the parameters A and D are restricted to be on these ellipses. And this case is a three-step nilpotent derivation. And there is this fourth case here when the derivation has complex eigenvalues. So it's just again a matter of computation to show that metrics corresponding to cases 1, 2, and 3 are algebraic Ricci solitons, but the case 4 is not an algebraic Ricci soliton. But one can show that this metric is indeed homothetic to this one, and hence even it is not an algebraic Ricci soliton, is homothetic to an algebraic Ricci soliton, and hence is indeed a Ricci soliton, also not necessarily algebraic. And so finally, the case of R3 is where some differences with previous situations appear. And the main difference is that we computed also, we determined all F critical metrics with zero energy in this situation, and they all are algebraic Ricci solitons, or otherwise they are homothetic to one of the following three families. I mean, I just wrote the equations here, but I mean, they correspond to derivations whose self-adjoint part has determinant different from zero and trace equal to zero. So this is, but this is just for giving the special values of the parameters. And so again, the thing is that any algebraic Ricci soliton is critical with zero energy, but there is also these three metrics here, which are these three families, which are not algebraic Ricci solitons. And for example, in the previous case, even though this was not an algebraic Ricci soliton, it was indeed a Ricci soliton. Now the question here is whether these three families, which are not algebraic Ricci solitons, whether they may be Ricci solitons or not. Okay. So in order to do that, we compute the critical value for homogeneous Ricci solitons. So this is the value of the parameter T, which makes for which these metrics are F critical with zero energy. And the situation is that we may have either these symmetric spaces, and in these cases, this parameter T is either -1/3 or -1/2. We may have the only Ricci soliton on the semi-direct extension of the Poincaré group, which corresponds to the parameter T equal to -1. In the case of the semi-direct extensions of Heisenberg, either T is equal to -3, -3/2, or it lives in this interval, -3/4, -1/4. And in the case of algebraic Ricci solitons on the semi-direct extensions of R3, then the critical metrics also correspond to T equal -3, -3/2, or they live in this interval, larger interval, -1, -1/4. So the three examples I showed you before in the previous transparency, they correspond to this interval here. In that case, the value of T is always strictly less than -3/2. So there are still a possibility for this matrix when the t is equal to -3 to be homothetic to one of these algebraic Ricci solitons. And thanks to the work of Romina Arroyo and Ramiro Lafuente, we know that these are the only possibility, because if they are Ricci solitons, they have to be homothetic to an algebraic one, and this value is invariant by homothetism. And now the thing is that one goes one step ahead and computes this third order curvature invariant, and it distinguishes the different possibilities for t equal -3. So the values, admissible values for these two algebraic Ricci solitons do not correspond to the admissible eigenvalues we may have here. So the situation is that in dimension 3, we have an equivalence between homogeneous Ricci solitons and a critical matrix with zero energy. And in dimension 4, we have such an equivalence up to the possibilities which may occur here in this situation. So this is still a work in progress, and there are quite a number of open questions as concerns critical metrics on semi-direct extensions of the Heisenberg group and the Euclidean group, but it seems that the equations are maybe too difficult to solve, or at least we were not clever enough to choose the best orderings in order to make use Grosvenor basis, which allow us to get simpler polynomials in these situations. So I think this is essentially what I wanted to tell you. So thank you very much for your attention.
So is there some questions?
What is currently known about homogeneous four-dimensional manifolds that are Bach flat?
Oh yeah, for the Bach flat, the situation is very clear. I mean, it's in the four-dimensional case, there are exactly 5 families of Bach flat metrics. 3 of them are indeed conformally Einstein, and there are exactly 2 Bach flat metrics which are not conformally Einstein. And one of them is in these semi-direct extensions, and the other one is in the semi-direct extension of the Heisenberg group. So let me say the conformally Einstein ones corresponds to one of them is in a semi-direct extension of the Heisenberg group, which is a self-dual homogeneous metric, and the other 2 are in semi-direct extensions of the abelian group, and all of them are conformally Ricci flat. And then there are 2 other families living in the E11 and in the Heisenberg group, which are strictly Bach flat. They are not conformally Einstein in no case.
Thanks.
Is there other questions? So I have one. So sometimes on certain example, you find families on critical metric depending on T, and you have extremals of the intervals. Does the solutions at the maximum point on the interval or minimum point on the interval satisfy something special?
Yeah, in some cases the extremal points. So let me show. For example, in the case of so the situation here. In the case here, for example, you have all these intervals. So the extremal points here, this is the only metric on the Heisenberg group, and this is just the symmetric situation. So, for example, in this for these intervals, this is clear. Here, for this interval here, so this is the critical metric on the geometry sol 3, and then this one here corresponds to -1/3. But I think in most cases as well, for example here, we do not see any special relevance of these functionals. So there are some cases that the extremals on those intervals, they have a special geometry, but there are other situations where we couldn't detect any special situation on those cases.
Thank you. So if there is no more question, we thank you again. Now this is the end of the conference, so it's a pleasure for me to have the opportunity to thank Giovanni and Andrea for having make all these efforts so that we can meet here and enjoy the mathematics.
Okay, so thank you all for attending, and especially to the speakers, so for having accepted the invitations and making all effort really to prepare wonderful talks and lectures. So thank you very much.